University. He did his PhD from University of Berkeley in 2023. His lab, CMU AI and Reinforcement Learning Lab, is interested in a broad range of topics ranging from core reinforcement learning algorithms to scaling RL methods to foundation models to real robots. So today, he'll be talking about train time and test time exploration in language models. Over to you, Viral. Thank you.
Thank you for the introduction and thank you for having me. And thank you all for coming. I guess it's probably very early in the morning for you all, and on the last day of the workshop, so it's probably already quite tiring. So today I'll talk about train time and test time exploration in language models. This is going to be actually focusing a lot on things involving reinforcement learning, and I'll actually tie back a lot of the ideas I'll talk about to like more classical RL ideas. And see like how kind of some interesting new challenges emerge, as well as like how existing methods actually can sometimes be quite limiting when you think about language models from a traditional RL sense. So my goal is hopefully to give you that broad landscape for this intersection of RL and language models by thinking about this problem of exploration today. Okay, so let's get started. So we know that currently language models or large language models, they do a lot better when we can run them for longer. So rather than, for example, querying a language model on a given question, if we can instead let it run for longer, let it think for longer in a way that kind of performs useful computation or does reason, we know that this sort of kind of scaling of test time compute, meaning thinking for longer at test time when given a test problem, kind of generally leads language models to do well. So hopefully the answers tend to be right and they can generalize really well. So this is sort of the core technology behind a lot of major advances in language models over the last 1 to 1.5 years that we have seen. Now, what is kind of the key object of interest for today's talk is going to be how can we train models to do so? And sort of at a very high level, the core technology or the core technique that goes into training models to be able to reason or scale test time compute is fine-tuning them or post-training them with reinforcement learning. In particular, this is actually on-policy reinforcement learning. So just to kind of show you what that looks like, you often end up taking a data set of prompts or data set of questions that are given to you. And you have some notion of checking correctness of a particular response from a model on top of those questions. So this could be in the form of just a reward function that tells you what the final answer is, and you can kind of just do some basic minimal answer checking against that final answer. And what you often pose, the RL problem that you often pose looks like the problem of maximizing this reward function, maximizing the correctness of the final answer that the model produces after a bunch of reasoning, after a bunch of long chain of thought that it produces itself. And this is typically solved with on-policy RL. So it kind of looks like the following little cartoon where you start from the problem, you produce a trace by generating one token at a time. And hopefully, if the trace ends up with the right answer, you kind of get a +1. And if not, then you get a 0. And you'll just apply a reinforce or PPO style objective to train this. So the key question that sort of has motivated this line of work in my lab has been, how can we continue to enable improvements if we keep on doing RL on more data, maybe with bigger models, maybe on more complex problems? And to answer this question, I'm going to talk about how exploration is the key bottleneck that comes in when you think about scaling up RL and making it possible to kind of get more and more benefits from reinforcement learning training. So to start to kind of think about this problem, let's actually just kind of take a very kind of top-down view on what an RL algorithm in general entails. So at a high level, there's actually two mechanisms or two sort of properties of an RL algorithm. The first one is exploration. So you often build techniques where you can go and collect data. That's exploration. And there's exploitation or learning where you can learn on top of the data. And this often results in sort of the right kind of loss functions that you're going to make updates on with, you're training your neural network on, for example, a Q-learning loss, a policy grade loss, etc. And we know that these two things are in conjunction or they intertwined with each other. So exploration gives you data for exploitation. Exploitation affects exploration subsequently. And all of these two mechanisms now form the basis of any RL algorithm. Now, if you think about what, so this is a very idealistic picture of an RL algorithm. But if you think about now what happens for when you replace your models with not tabular models, you move to deep neural network models, then what ends up happening is that exploitation gets replaced by sort of defining the right kind of objective function, and a lot of nuances of deep neural network optimization come in here. So for example, we know that Q learning or TD learning or these kinds of algorithms, they're not quite convergent, or provably convergent with deep networks. So now a lot of challenges around how do you make sure your optimization is behaving stably, how do you have replay buffers, et cetera, all come into the picture for making sure that your algorithm can behave well. Turns out that in LLMs, though, there's a little bit more nuance where, there's always the question of exploitation in the form of designing the right training objective and having the right optimization algorithm. But now exploration actually takes a little bit of a different form. So in traditional deep RL, you would still go and collect data by running your policy in the environment, maybe with a certain exploration strategy. But now in LLMs, there's actually two forms of exploration. You'll have to do exploration at training time, meaning you'll have to explore the space of possible trajectories or responses that your model can produce. But also you can explore at test time by potentially letting the model run for longer and do interesting stuff in its chain of thought. And this is a slightly different mechanism from like the kind of mechanism you see during, in traditional deep RL where there's an environment and you're optimizing reward in that environment. So what I'm going to talk about today is like these two notions of exploration. So one of them is train time exploration, and I'm going to call it exploration, the default term. And the other one is going to be test time exploration, or what I'm going to call extrapolation, because you're going to let the model be trained on episodes of length up to h, and you're going to let the model run for lengths much longer than h at test time to produce a response to a question. So the first part is going to be based on train time exploration. We'll discuss how can we actually get models to sort of to learn to do behaviors that these models don't have access to or don't have from pre-training. And this will be based on ideas from steering models based on guidance. So I'm going to talk about what that means in a second. And the second part is going to be based on test time exploration or extrapolation. But the idea is, can we train models to spend more compute at test time and do better and better as they spend more compute at test time? So that's going to be the second part of the talk. Okay, so let's start with the first part on exploring at training time. This part is based on two papers. The first one is this paper called RLAD that you can find on arXiv today. And the second one is a paper that, it's not a paper yet, it's a blog post that we put out on the CMU MLD blog. It's also a paper that we hope to put out very soon. So you can also read a much more detailed kind of paper as well. But the blog has many of the results that I'm going to talk about today. Okay, so to kind of ground this part of training time exploration, we'll talk about this challenge of training on hard problems. So what is a hard problem? A hard problem is a problem or a prompt where the pass at k of the base model is 0 for a very large k. So what do I mean by pass at k? So let's say you take a base language model and you end up querying it on a given input prompt, a given input problem, which is, let's say for this discussion, consider it's a math problem. It's a question in math, which has a final answer, a numerical or a regular expression based final answer. And what you do is you query this model or query the base model that you have access to on top of this question. And now what you do is you can obviously measure the correctness of the final answer that your model produces by comparing it against the reference answer. But what you can also do is you can also sample, you can give this base model multiple attempts. So you can give it, let's say, k attempts to solve this question, k independent attempts to solve this question. You can think of this as k episodes that you run during RL. And you can measure if any of those episodes were correct at all. So that refers to this pass at k score. So pass at k can be thought of as the probability that your base model is going to sample at least one correct rollout on your test question within k independent attempts given to it. So problems or prompts where you cannot get any single correct answer in k attempts for a large enough k can be thought of as being hard, because these problems you cannot get any reward when you roll out your model. So all of your episodes or all of your traces end up getting no reward and end up failing, in which case you cannot really do any kind of RL to improve your model altogether. So these problems tend to be quite challenging because in general, when you do RL on top of language models, if you cannot sample any correct rollout, you're not going to get any signal, which means you're not going to train your model altogether. So for our purposes, we're going to think of this k being 128, which is a fairly large number. Most of the problems that we train on typically still get a pass at k score where k is set to 32 to be non-zero. For our purposes, we're going to consider training on problems where pass at 128 is equal to 0. So hard problems are special because there's no learning signal, as I mentioned earlier. And even if we can sample a correct trace accidentally out of stochasticity of the model, turns out that this correct trace is quite different from the kind of traces that your base model is going to produce. So it's often very hard to learn from this data altogether because you're already starting off with a base checkpoint, which has certain kinds of modes of behavior. And this particular trace that you ended up sampling is very different from the kind of trace that your base model is likely to produce. So it's very hard to fit this data altogether. Okay, so theoretically speaking, this problem actually looks a lot like an exploration problem. So why does it look like an exploration problem? Because exploration typically refers to the mechanism which allows you to discover reward. And in this particular case, where pass at k is 0, these are precisely problems where there is no reward by simply doing on-policy rollouts from your model. So being able to learn on top of this problem set is kind of like an exploration challenge where you need to find a way to discover reward in the first place when you roll out from your model. So what you can do is you can take inspiration from classical methods in RL to do exploration and apply them here. So we tried that. And one of the simple things that we tried here as a first step was to take methods like adding stochasticity or adding entropy bonuses to your exploration distribution, to your model as a regularizer. So what you can do is you can maximize reward, but also add a little bit of an entropy term to hope that the model now ends up sampling more stochastic tokens and it accidentally hits the right answer and gets a reward and starts to learn from it. So we tried this. The idea is just like, let's say at a particular node, you would want to now sample a slightly different token in hopes that you can potentially succeed. So you provide a bonus for sampling novel tokens. When you do this, it turns out that so this idea can often work very well in simpler tasks, especially if you choose the decay rates of this bonus term properly over the course of learning. But it turns out that if you do any of this sort in the case of LLMs, you find that you don't actually improve exploration altogether. So what I'm showing here in these plots is I'm measuring as a function of RL training on the x-axis. I'm measuring the percentage of problems I end up solving on the left plot, and the entropy of the next token distribution of the model on the right plot. And you can see that the entropy actually goes up in the blue line compared to the naive RL run, but you don't really improve the solvability of any of these hard problems. So, over the course of learning, if naive RL without any entropy term could have solved 6% of the questions, you're kind of roughly at the same level with entropy as well, and it's sort of all overlapping without any meaningful gains. So clearly, just adding an entropy term does not quite work here. The other thing which you can do, which is which resembles a lot more of ideas from sort of deep RL as opposed to sort of classical tabular RL, is to go and perturb, for example, how much do you trust your more optimistic updates in your policy gradient loss. So if you are familiar with, for example, a lot of losses that we use for training language models, they kind of look like this PPO in style loss function where you have some importance ratio weighted advantage terms, and you clip that importance ratio in between some thresholds. And turns out that one kind of way to explore in these kinds of PPO-esque objectives is to just set epsilon high, or the clipping ratio on the higher side to be more, or clipping ratio on the positive side to be more positive, as opposed to the one on the lower side. So if you set epsilon high to be higher, you'll end up exploring a lot more. So we tried this approach as well, where we ended up using a larger epsilon I to allow for a more aggressive, more optimistic update. And if you do so, we again found a similar trend where the entropy blew up again. So it was clearly exploring in the sense of being more stochastic, but clearly the percentage of solvable problems was not increasing altogether. So it's again at the level where it's the same as the default run, which does not have any of this term, any of this mechanisms added to each other. So what did we learn from these experiments? So what we learned was classical exploration methods did not end up improving some notion of solvability of problems, which were very challenging. And this makes sense because they did explore in the classical sense of adding of novelty or visiting novel tokens, but these novel token sequences do not encode meaningful semantic priors that we already have in base models. So when we think about fine-tuning a base model, we're not starting from scratch. We already have some priors, and we want to be able to explore in the space of these priors as opposed to being just producing arbitrary token sequences, which these methods encourage. And oftentimes what ends up happening is that these methods do encourage covering more tokens. And in theory, they could lead to the right set of tokens, the right sequence of tokens if you sample enough from them. But in practice, what happens is this often leads to sort of optimization challenges, because remember, with every single token sequence you sample, and you make update on your model, you're kind of making your model diverge from the initialization it started off from, which can actually lead to your model suffering from things like forgetting and so on. So there's some tight kind of interplay between exploration and learning, and that interplay causes your model to potentially run into optimization difficulties and instabilities if you do this with random sequences altogether. So the obvious other alternative you can ask now is, well, since you already have a base model, can I go out there and actually transfer semantic priors from easy problems to harder problems? So let's say if I train on simpler tasks, my hope is maybe a curriculum of some sort can now give me like benefits on harder problems, which I could not solve before. So we tried that as well. So we tried exploration via transfer. So we tried to train on some easier problems and now hope that the kind of skills or policies that were learned on easier problems can somewhat generalize to harder problems, presumably because these models already have rich priors that will allow this kind of transfer. So we tried that. And we find that when you mix in some easier problems in your training set, so easy means kind of somewhat easy problems, easier means really easy problems, you do find that you can actually optimize your reward on top of these easy problems as a function of RL training really well. So this is just like the set of measurements we do, and we kind of fit a curve to them just to kind of get more cleaner signals. But on the other hand, what we found was on hard problems, that's not quite the case. So like training on easy problems does help you optimize reward on easy problems. But these policies or behaviors that you learn on easy problems don't quite help you increase solvability on the hard problems. So there's no apparent gains in solvability on the right-hand side as a course of training. In fact, what we also found was, while arbitrary easy problems do not enable exploration on hard problems, it also happens that this picture is a bit more nuanced. So you can also go and train on a mixture of easy and hard problems with RL. And you can measure some kind of pass at K for a higher value of K than what you were training with. And when you do that, you will find that actually, if you train on a mixture of hard and easy problems, like the green line that we show up here, you'll find that the reward or the success rate on a held out set of problems kind of plateaus much quickly compared to when you train on only hard problems without any easy problems mixed in. So hard plus easy plateaus, while hard does not quite plateau. This means that there's not just a lack of a transfer problem, but there's actually a negative transfer that is happening where training on easy problems inhibits your learning on harder problems altogether that you see up here. So there's some kind of a negative transfer, as I mentioned. So turns out that this negative transfer can be very neatly formalized under this notion of what you can call ray interference. And it's not something that we call it. There's a paper from Tom Scholl et al. In 2020 that's called ray interference, a source of plateaus in deep RL. And what this paper says is that, well, if you optimize with RL, let's say on two kinds of prompts or two kinds of tasks, some tasks where it's very easy to get reward and some tasks where it's very hard to get reward, what ends up happening is that the trajectory that RL or on policy RL kind of follows when optimizing this joint objective looks like the following. So, let's say you start from a base model, which is one of these points. So what I'm doing here is I'm just simply trying to visualize over the course of on policy learning for different checkpoints that I see, what does the value of J easy and J hard look like? So J easy just means reward on or average reward on easier problems. J hard is average reward on harder problems. And I'm just measuring over this 2D plane. I'm just trying to trace the trajectory of optimization as I do on policy RL on this objective that you see up here. So what ends up happening is when you start training from a base model and you're now running RL, the ideal desired path is, well, as you run RL, you can improve your reward on both easy and hard problems and follow kind of this roughly kind of diagonal line going away from the origin on this plot. But what ends up happening often is that your RL runs, especially with on policy RL, follow a very jagged path, a path that potentially optimizes J easy a lot more initially, maybe even at the cost of J hard, and then eventually start to optimize J hard after that point. And a lot of these curves often get stuck when they have optimized the easy problems up to enough degree, and they kind of just stay there, and that kind of often reflects as a plateau in the learning curve that you see, and that's why the name a source of plateaus in deep RL. So this sort of a phenomena makes it very inconvenient for RL to actually optimize on a harder problem set when you mix in easy and hard problems, because Now you are kind of just stuck at the solution that optimizes the easier problem without making any progress on the hard problem as much, and maybe even degrading your performance on the hard problem, as you just saw on the previous slide. Turns out that there's actually a lot more work on trying to address this issue by, for example, kind of a line of work which tries to optimize for this pass at case score directly. And a lot of that work actually still runs into the same problem of interference, because all of that work kind of roughly at a very high level amounts to simply mixing in together J easy and J hard with a different weighting on top of them. But a weighting which where both the coefficients are positive and sum up to 1, for example, is not going to ever let you kind of, it's going to change maybe the curvature of this path that you see up here, but it's not going to get you this, get you around this behavior of like, getting sort of a synergy that takes you in the positive direction on both of them jointly. And that's why it does not quite solve the ray interference problem. It does still exist, but maybe sort of just gets a bit mellowed down for us. Okay, so what can we do finally, right? So I mean, we saw that classical exploration methods tend to be overly random, and exploration via transfer, which in some way or the other is probably transferring semantic priors that you've learned on easier problems to harder problems, does not quite work because it runs into this interference problem that I just showed you. So what can you do in the first place? So our approach has been quite simple towards addressing this, and I'm going to show you 2 instantiations of this idea, and I'll show you like some results that kind of emerge out of it. And it turns out that it sort of still relies on semantic information in base models, but avoids this interference issue that I talked to you about. So what does our approach look like? It looks like this notion of guided exploration. So what do I mean by this? The idea that we have, the main high-level idea that we have is to now train the base model using some kind of guidance from off-policy or Oracle data to guide this on-policy exploration issue, to guide the on-policy exploration during learning in the first place. So just to show you a quick example, let's say if given a particular problem, which is shown as this black colored node that you see up here, if all of my traces on this particular problem ended up being incorrect, so all of them ended up in a red colored eventual outcome, what I could do instead now is I could condition my generations on policy on a set of extra nodes or a set of extra like tokens, which you can think of as guidance provided to you from some external source. So the hope is like now, condition on this guidance and the problem, so these orange nodes and the black colored node, now you can actually get on policy RL to succeed, and you can hopefully reinforce good behavior that you are seeing. So the key question now that you can ask is, well, what are these guidance nodes that I introduced here in this picture in the first place, right? So we have 2 instantiations of this idea. The first instantiation is this notion of what you can call reasoning abstractions. And you can think of this as basically some kind of statistic generated from off-policy solutions that exist on this data. So you can think of now, so I showed you this graph that before. What you can do now is you can go and ask humans, for example, to write down solutions for you. You can ask other models to generate potential reasoning traces on top of your question. And what you can do now is you can ask, you can take all this data that you have access to, and you can try to find out some common patterns that exist inside of these traces. So you can go and ask a model to like potentially summarize a lot of solution traces or solution attempts given to you. You can ask a model to potentially rewrite a human written solution into particular bullet points that you can potentially use. And you can do all of these things jointly together. So what you're doing is you're taking a bank of correct and incorrect solutions on a given question, summarizing key insights from them, and using them as these nodes that you see up here. You can also go and train them. You can also go and train a language model itself to generate these summarized abstractions in the first place, but these are just natural language summaries that you can get in any way possible. And you can condition on them as guidance and let the model go and continue from there. So the way to think about them is to think about this as a hint that is given to you to potentially generate a successful on-policy rollout on this given question. Just to give you an example, like this is a math question that exists in one of our training sets. And here the reasoning abstraction looks like something that talks about a generic property of what the definition of least common multiple looks like in this particular setting. And it shows you an example, and your solution now can be conditioned on top of this abstraction. So in our prompt, we we refer to an abstraction as or this abstraction as a cheat sheet. So you can see that that when the model goes and solves the question, when it does on policy exploration conditioned on the question and the abstraction, it refers to this abstraction as the cheat sheet and applies a similar rule that was described in this abstraction box in its own solution. So it's kind of using the ideas from here and it's able to succeed on this question, whereas by default, it's not able to succeed. The other thing you can do, which is much more simple, and this has been something that we've been more recently excited about, is to just use reference solutions. So here in the abstractions approach, we took a bunch of solutions, tried to summarize common ideas appearing in them. What you can also do is you can simply take reference solutions. For example, let's say if you have a human written solution to a math problem, which turns out is abundant, but we don't typically use for on policy RL because it's not on policy in any way. What you can do is you can now just take these reference solutions written by humans and just ask the model to kind of build upon it. So what you can do is you can just take a partial solution that a human might have written for an Olympiad question, condition on top of it, and let the model continue from here. And now it's more likely to succeed because it's shown a little bit of a solution and it's kind of put on the right track in some ways, from which it's more likely to succeed than when it's not given that. So that's sort of the simple other approach, prefixes of reference solutions altogether. An obvious question that comes up when you think about using prefixes of reference solutions or reference solutions in the first place altogether is why not simply imitate these reference solutions in the first place? So if you think about like expert demonstrations from a traditional RL standpoint, the most obvious solution to learning from them would be imitation learning or BC, behavioral learning. So why not just simply do SFT or supervised fine tuning on these reference solutions? We tried that as well, and turns out that if you do so, you're kind of somewhat going to be reducing your performance a little bit. So your SFT plus RL style approach, where you SFT on top of reference solutions and then try to let the model improve on policy, is actually a bit worse than simply letting the model learn on policy on hard questions. So that's the light blue versus the dark blue line that you see up here. And it turns out that this often happens because training your model by imitation learning reduces its entropy on a narrow set of tokens that the imitator produced, that the expert produced. And that results in kind of crippling of your exploration during RL. And the main thing to note here is that these traces that a human wrote down are very different from the kind of traces that your model likes to produce, because a reasoning model is going to go and like try to produce a long output response, which is going to do all sorts of crazy things. Whereas a human written solution is likely going to be very underspecified and very kind of like short in some way or the other. And these stylistic differences actually lead you to thinking that, when you try to mimic human solutions, you're going to reduce your model's coverage so much that now you're not going to be able to improve any further from there. And that gets reflected in the token entropy. So earlier we saw entropy blowing up. Now entropy goes down and becomes too low for your exploration altogether. Whereas using this notion of guidance during or reference solutions to provide guidance during RL actually boosts solvability of problems, as you can see in the orange line. And the entropy is kind of much more stable in some ways. And you might be thinking that these values are kind of low, the differences are kind of low between them. But this actually makes a huge difference because a small change in entropy per token gets compounded massively over longer responses. Like imagine 32,000 tokens that you're producing, even a 0.02 difference gets compounded a lot in the diversity of the entire response that you produce. Okay, so our approach, as I mentioned earlier, was just very simple. You take your current RL checkpoint, you're going to provide to it some fixed sort of partial guidance from a reference model, from a reference solution, and you let it now continue solving the question given this guidance. Now, on this hard problem, as I defined earlier, the pass at k of the base model is 0, which means the base model has no success rate altogether at solving this question in the first place. But turns out that one thing we observed in our experiments is that once you end up like training your model conditioned on guidance, the model that you produce is now able to actually succeed at producing solutions to those questions, even when guidance is not provided to it. So there's some interesting transfer that happens where you have trained your model to do on-policy learning, conditioned on some little guidance or partial prefix of your solution, but now it's able to succeed at producing traces which start from the question without any guidance altogether. So there's some notion of transfer between the guided version of the prompt to the unguided version. And by the way, we call our method POPE, or it stands for Privileged On-Policy Exploration. So privileged because we use reference solutions for guiding the model a bit. But an on-policy exploration because all of the learning that you see is happening on policy. You never make updates on off-policy reference solutions that were given to you in the first place. So why does this happen, this transfer that I just talked to you about? It happens because, so I'm not going to too much detail about this, but what we show in our experiments as well is that this happens when you have models that can follow instructions really well. So typically when we think about language models, we think of them as being capable of following instructions. So you can prompt them to potentially build upon a particular solution. You can prompt them to potentially revisit guidance that appeared inside of a solution. And turns out that when your language models can follow these instructions really well, even if you give them a fixed prefix of a reference solution, they're going to be able to like backtrack to some ideas inside of that guidance and start to solve the question from there, which ends up like enabling this transfer that I talked about, where you've trained the model only to solve the guided version of the prompt, but it ends up transferring to the unguided version because the model is able to now sort of, you can instruct the model to do so by asking it to revisit ideas that appeared inside of this guidance or inside of this partial solution that you gave it in the first place. Okay, so and you can think of this as sort of what you can call an asymmetry between instruction following and reasoning. So what you're doing here is your model has no capability of solving a very hard question, but you are using the fact that instruction following, like you can, is much easier for a model than to just reason about a hard question. And you're using instruction following to kind of produce training signal for the reasoning ability of the model. And you can think of this as sort of an asymmetry between, or asymmetrical competence argument, where language models trained on internet data are good at doing instruction following, although they're not good at doing the best computation to find the right answer. And one ability is used to supervise or guide the other ability of the model. And hence this word asymmetry that you think about here. Okay, so just to show you some empirical results really quick, we found that actually, so I showed you this plot earlier too, where when you mixed in easy problems on your hard problem set, you found that the models did not make much progress on this pass at 32 metric at test time, as you continue to do RL training on the x-axis. What we find is that now when you add in like guidance into these hard prompts, you see that the performance on hard set actually improves a lot more. So that's the kind of red and pink lines that you see compared to the blue line, and compared to when you add in easy problems, which is the green line. In fact, when you add in easy problems and the guided guidance as well, that actually improves performance over the green line a lot, which is the pink line that you see up here, and it's better than the hard set also. In terms of just some concrete numbers, we find that adding in guidance actually leads you to the highest numbers on top of the hard set, or an IID hard test set, on top of the AME and HMMT benchmarks. So these are more standardized benchmarks that you see. And you also get a lot better performance on these harder problems that you are training on. So better on standardized benchmarks and better on harder problems altogether as well. In the paper, actually, which is going to be out hopefully soon, we also show that you can actually measure the amount of ray interference as well that I talked about earlier. So on the easy problem set, when you mixed in hard and easy, you got this ray interference problem. Turns out you can measure that on this set when you add in guidance, and you find that you actually make updates which are closer to the diagonal. So you are actually improving on easy problems as much as you're improving on harder problems when you mix in this guidance altogether. So that's quite nice because it's a very clean conceptual example which shows that you can avoid this interference problem by using this guidance as well in the first place. Okay, so that was part one. So the main takeaway from this part is to think about exploration as being different from classical exploration methods because they just lead to diversity and that can often destabilize optimization. Exploration is also being different from just learning to transfer information or transfer knowledge from easy to hard problems because that turns into interference. And one simple way of doing so was to rely on sort of the instruction following ability of a base model to steer it in the right direction and learning from that guidance data that I showed to you here, which is our method called POPE. And we did really well on kind of avoiding these optimization instabilities while still learning to improve performance on harder problems that you see up here. Okay, so the next part of this talk, I'm going to talk about exploration at test time. So far what we were thinking about was learning on problems where during training, you cannot sample a correct rollout. But now what we want to do is we want the model to potentially think for longer at test time and do better and better. So the exploration is happening inside of the model's rollout on a given test problem that you see. And this part will be based on 3 papers, or actually 2 papers. One of them is called E3, that's on arXiv already. And it's sort of our first effort in this direction. The second one is this paper called Reasoning Cache, which is going to be out on arXiv this month. But I'm going to talk about it still because I think it's great to talk about ongoing work at workshops. And the third one is going to be is a blog post that we put out last year in January on optimizing test time compute and how it relates to this notion of meta reinforcement learning, which is kind of very much tied to this question of exploration at test time in my head at least. So you should check out that blog on the CMU MLD blog out there. Okay, so the main question that we are kind of interested in, technically speaking, is this question of running the model for longer and having it do better on a test problem. So ideally, you want your model to be trained, let's say, at a particular horizon length. So it's probably trained to produce episodes or reasoning traces of length h, but you want it to be such that it should be able to learn skills that allow it to now run for longer on a harder problem at test time and still do better. So in general, like you're obviously when you run on policy RL, you're going to set an episode length. And in typical RL as well, where we assume, in many cases, we assume in deep RL that we have an infinite horizon discounted formulation for the RL objective, but we never really run infinite horizon rollouts. We often clip them at a particular maximum episode length. But then the hope is that, well, if the agent is run at test time when we are evaluating the policy, when we run the policy, the hope is that now the policy can potentially succeed. And that does happen because in traditional RL, you often make Markovian assumptions altogether. In LLM RL, you are not quite Markovian because you preserve the whole context that the model has generated so far. So it's technically not Markovian. So what we want to do here is we want to be able to now learn at a particular value of h, but then hope that now the model can generalize to a harder problem and produce and do meaningful computation at much longer output lengths as well. So more concretely, you want to make sure that you care about optimizing performance or optimizing reward on a given test problem when your trajectories or traces of z's are produced by the model. And the hope is like, well, you're still optimizing your training objective. So you're going to train for this implicit objective by optimizing on the training set. But the difference is that now at training time, you have a much smaller maximum episode length here, whereas at test time, you want the model to make progress or maybe optimize for reward at a much longer output length altogether. So Z's are different in lengths. And this is what is the problem of extrapolation here. So it turns out that currently, when you take models that are out there in the open source world, they don't quite extrapolate really well. So this is a little experiment from one of our papers, which shows that if you take models that were trained with RL or supervised fine tuning and you run them for longer on a test set of hard math problems called AMY 2025, you find that the accuracy increases initially when you let the model run for longer, but then it plateaus really quickly. For some of these models, the plateau happens much sooner than later, and you are not able to actually improve performance beyond that point. So these models don't really extrapolate well. So the key question that we had was, well, how can we think about this question of training models to extrapolate in the first place from a more first principle standpoint and actually build a method that will work really well in practice. So that's sort of the main goal. And remember that the train and test objectives are a bit different. So at test time, we care about performance of the model on longer h, whereas at training time, we have fewer tokens. And also the other difference is that, well, we care about test problems, which we probably are not given, and maybe they are also from a different distribution compared to the training problem set in the first place. So we care about evaluating performance at greater than h tokens at test time, at h tokens during training time. So the first thing you can do, and we did some work on this actually, was to go about this problem by simply massaging the training objective a bit differently. So for example, you can go and instead of optimizing for the correctness of a whole answer produced at the end of a reasoning trace, you can go and optimize for a slightly different objective that optimizes for some notion of progress. So, well, it's kind of like getting into the territory where you're trying to make this problem be a little bit more Markovian than typical. So usually you would produce a long episode and give a reward only at the end, but now you can give rewards at intermediate segments of your reasoning trace that the model is seeing. So you can think of that as sort of giving you rewards which are slightly denser than rewards which are just very sparse at the end of the whole trace altogether. So you can think of this as a progress reward or a process reward in the language model community as well. And this sort of an idea does work. So you can we had a paper on this at ICML last year, which showed that you can do this kind of thing. You can also connect it to ideas from meta reinforcement learning, and you can build a method that actually does improve performance overall in the first place. But obviously, I guess it requires you to design this progress reward really well and maybe handle a lot of other little quirks of implementation where you are adding dense rewards into an LLM training framework in the first place. The second approach that you can do is actually go and change the training data. So one question you can ask is, well, why do I care about more than H tokens at test time in the first place, right? And the answer to this question is the fact that, well, at training time and test time, you have different sets of problems. Test problems could be considerably much harder, and hence you might need to spend more tokens to get to the right answer on the test problem. Whereas on the training set, you kind of don't need as many tokens. Now, if you could cover the distribution of test problems during your training as well, suppose, then in principle, you can argue that this difference between the length of the responses will kind of diminish a bit, at least to some extent will diminish. So a lot of times what ends up happening, especially at industry, is that folks end up training models at a fixed response length of H tokens that they predefine. They're going to also like test the model at the same response length, but they're going to try to cover the training set or cover the test set in over the course of their training. So they're going to, in some ways, like try to overfit on the kinds of problems that you're going to see during test time. Not the same problems, but at least the kinds of problems, in hopes that now, well, if you're trained on the sorts of problems at test time, at training time as well, then maybe you don't need more than H tokens at test time when you deploy the model. So this is kind of a bit unsatisfying because in theory, there's always a very different test problem, which I probably need to run longer episodes on. And that's kind of not being trained at all because you're kind of like trying to generalize by overfitting, but that's only going to take you to some extent. So the third thing that you can do actually, which is where maybe our innovation comes in, is to think about doing this, is to think about solving this objective a bit differently, where you go and you try to change the distribution of Z's that you sample during training so as to kind of minimize the difference between these two objectives. So the idea is, well, if you can change the distribution of Z's altogether, then in sort of more fully connected MDPs like reasoning, where there's no external environment and you can reset anytime you want to, changing the sampling policy, changing the policy which samples the Z, can definitely provide you with ways to enable extrapolation. And I'll show you kind of two examples of it, depending upon the time, but I'll show you at least one in detail and one sort of a bit more quickly. So there's also some nice connections between this and optimization in a POMDP, which I'm not going to go into too much detail, but if you're interested, I'm happy to talk about it after this talk. Okay, so the first thing I'll talk about here, the first way of changing the sampling distribution is to use this, is from this paper that we call E3, that actually structures the kind of extrapolation that you see. So simple idea here is to think about this notion of chaining of skills, chaining of high-level skills that leads to extrapolation. So if you think about a base LLM as producing, as being able to produce different segments of responses that do different tasks. For example, maybe you write down a little proof of a little step in a particular question. You maybe go and try to now verify whether that proof is correct. And if it's not, then you end up revising something. Then these are basically skills that your model is chaining in the first place. So if you run RL on top of such a model, the model will now be able to chain these skills together. And it's also going to be able to potentially chain many of these more in the first place to extrapolate a lot better. So, for example, chaining, for instance, when you train your models, which have these priors for chaining, these models will end up, for example, doing many things together. They'll end up learning to verify a generation. They'll end up learning to revise a generation, condition on the verification output. And these skills are relatively more local. Revisions much later down the line in a reasoning trace probably don't depend on something that came much earlier in that reasoning trace. So these are kind of slightly more Markovian. They lead you to producing more Markovian-esque representations in your whole reasoning trace. So if you can actually learn these conditional distributions, which are fairly local, you can hope to extrapolate because now you can, even if you have learned them from a fixed length of H, you can potentially generate rollouts that are much longer than H. And as long as they can make these local things, they can do these local things right, you'll be able to produce and make progress at longer lengths. So hopefully you can now stitch many of these things together to do multiple of these operations to succeed. So that's sort of the first mental model that you can take, where chaining extrapolates performance. So chaining is one way where you can produce a sample, where we can train at much smaller lengths, but generalize the model or extrapolate the model to much longer lengths in the first place. So we did this. So it turns out that being able to do this in a way that does not require to bake in these notions of skills requires you to just do some kind of curriculum training in some way, and requires a base model that has some prior for training for these kinds of skills. And if you do so, you can actually get quite a big boost in performance. So we find that extrapolation does happen. For example, if you take a model that was trained on 8,000 token output length, so the horizon edge is 8,000 on some easy problems, you can now like run this model on harder problems at a 16K output length, and you find that there is a big boost in performance here. So like if I measure performance on a medium and hard set of problems, of a model that is trained on easy problems at a smaller token budget, like 8K token budget, you can now run this model for 16K and shift from 8K to 16K at this like little dashed vertical line. And you're going to find that the test accuracy jumps up suddenly. So you do find that there is an extrapolation thing that's gonna happen if your base model that is under consideration has this notion of chaining of skills that you see. And turns out that you can actually amplify this chaining by training on the right data at the right budget. So for example, you can train on the right output length on the right kind of prompt such that this chaining behavior is incentivized, because these behaviors are somewhat present in base models. You just need to do RL in the right way to amplify these behaviors in the first place. And we found that for doing that, you have to kind of train at the right budget and on the right kind of data. In this case, you see that training on the easy data at a reasonably okay budget actually leads you to learn these extrapolation skills. And now when you query this model on harder problems, you can let it run for longer and it'll end up still succeeding really well. So the idea here was, as I mentioned earlier, just some notion of curriculum learning. So you train on easy problems at a smaller token budget, you learn these basic skills, you amplify them. And then now in kind of a stage 2 of the curriculum, you're going to train on harder problems with a larger token budget. You'll end up chaining these basic skills a lot more that you've learned from stage 1. So you can simply do some kind of curriculum learning, and just this mental model of thinking about chaining helps you produce models that are going to be much more successful on much harder test problems at much longer lengths when you deploy them. And that is sort of the biggest learning of this work. So with this, we were able to actually train a 1.7B model at CMU. So it's all trained on academic resources, which actually extrapolates really well. So this is, we compared it on 2 benchmarks. So this is a math reasoning model. We compared it on 2 math competitions, AIME and HMMT in 2025. And what we found was that this model ended up, so it was the maximum length it was ever trained at, maximum edge it was ever trained at was 16,000 tokens that you see here. So everything beyond 16K is operating in this extrapolation regime where you're running the model for longer. And what we found was that compared to many other open source models that you see up here, including models which are 32 billion parameters big. So our model is just 1.7 billion parameters big. Other models are 32 billion parameters or 7 billion parameters. And what we found was that our model did attain a much better performance compared to them. The only one model that outperformed our 1.7B model was the S1.1 32 billion parameter model, and that too the gain was quite small. So it's like about 16 times or more bigger compared to what we have, but the gains were much smaller. And that too, it was only present on one benchmark. On the AIME benchmark, we were actually much better. So you see that there's better extrapolation if you just think about these like notions of skills in the right way and do the right kind of recipe with curriculum and so on, and you can do much better than many of these open models that existed. And all this was done on academic compute. So many of these models that you see up here were actually trained by like much bigger organizations. And I'm not showing you here, but there was like a lot of models from NVIDIA that had come out at that time, like their NVIDIA Nemotron reasoning 1.5B. And we were still kind of better than them, although we just did it as one of the papers in RL. So that was quite interesting, that systematically thinking about RL actually can give you a lot more benefits here. Okay, now the more recent thing we've been doing is to kind of push this even further. So like if you see here, the numbers of like tokens that we can extrapolate to is roughly in the order of like tens of thousands. So it's 32,000 tokens that we can do really well at if you just think about things more systematically. What we wanted to do was to go even further. So we wanted to go and have a model that can now think for maybe 1 million tokens and still keep on making progress. Although training at 1 million tokens is simply infeasible because you cannot instantiate RL with that long of an output length. And just infrastructurally, it's like really problematic. And from a more conceptual standpoint, we think about doing on-policy RL. and your horizon is 1 million tokens, it's going to lead to variance explosions, and that's like not a good idea altogether. So what we did was we actually tried to explicitly have a more Markovian structure in our process. So we ended up doing a simple thing where we, instead of optimizing for just samples from my on policy distribution, what we ended up doing was we ended up applying a little bit of a scaffold around how we sample from the model. So we ended up optimizing the performance. So this should not be p-test, this should be p-train here, but we ended up optimizing performance of or average reward on Z's or responses that were sampled by not pi theta, but by applying some kind of an algorithmic procedure on top of pi theta. So this alg is nothing but just simply like a little bit of a function that you can apply on how you generate rollouts on top of pi theta. And what I'll do is I'll show you a simple example of this alg that allows us to run training at the same fixed response length of h, but does really well. And this idea is what we call a reasoning cache, or RC. And the idea is very simple. It's just nothing but simply a multi-turn decoding algorithm, where instead of producing the whole long response in one go, you produce a response, then try to summarize it, then produce another response, summarize it again, and so on. So what you do is you take your LLM, you give it the input question. This is what we're going to call turn one. You end up generating an initial response. This response is not very long. It could be maybe 16,000 tokens long. It could be 32,000 tokens long. It could be something that's more manageable. You now take this response. You now ask your same LLM to, in turn two, summarize this response. So you ask it to like produce a shorter summary. So in our experiments, this response is around 16,000 tokens long. The summary is around 2,000 tokens long in most of our experiments. So it's a much shorter summary compared to the response. Then in turn three, you now discard this response altogether and you condition on the input question and this summary, or a cache is what we call it, and ask the model to continue from there. So the hope is that the summary actually consists of useful information that the response had produced in turn one, and you continue condition on this summary in turn three. Now, after turn three, you take this continuation, you take the cache that already existed so far, and you update your cache from there on. So this is a lot like sort of like maintaining a belief state of what your model is producing, and that's kind of this cache, except that this cache is now being represented as text. So it's just literally a summary of what your model has done so far. And you keep going like this for multiple turns, and you have a sort of a long trace. Now, in this particular setting, the way we generated these cache, this particular cache that you see, relied on the fact that we asked the model in, let's say, turn three or turn four to simply summarize whatever it has done so far. So we literally instructed the LLM to summarize stuff that we have done so far. So it turns out that this ability of following instructions, right? When we ask the model to summarize, if it does not summarize really well, then none of this idea can work. So it turns out that the role of instruction following capabilities of the model are really high here. So we found that actually if you take these instruction tuned models or instruct models, the ones that we show in black, the gains from doing the summarization during the course of training is actually a lot higher as you scale up your test time like horizon that you see on the x-axis on two benchmarks. It's a lot higher than when you actually have a model that is maybe more capable in terms of reasoning abilities. At 16K, if you see, the accuracy is higher for these two middle lines compared to the green line. But turns out that you cannot benefit from this notion of summarization altogether because the gap between them is much lower. So you only get very little performance gains when this cache comes from a model that cannot follow instructions, that cannot summarize well, because the state estimation is really bad in the first place. So it's very much analogous to how we do things in like POMDP / like how we compress history and so on. The next thing here is just about training. So the training is very standard, very much like standard on policy RL. So you'll take sort of a problem, you'll produce many of these rollouts which are multi-turn in nature. You're going to see some of them succeed, some of them fail, and you're going to simply do on policy RL on top of all of them with just a final reward that you saw. So just the standard RL training, but note that you're never training at a horizon which is much larger. You're training only at the horizon which is given by the maximum length of any of these responses that you see, which is much smaller than the horizon that you can run the model at, because you can run multiple turns of this algorithm at test time. What another interesting thing that happens is now you can incorporate some kind of offline data or replay buffer. So I talked about this notion of multi-turn summarization and generation. You can also, what you can do is you can potentially start from an offline cache that is given to you. So if you have summaries from your prior attempts, you can just instantiate turn one with that summary as opposed to like just starting from scratch. And this can be thought of as basically doing some kind of off policy RL where you're maintaining a replay buffer of prior attempts, summarizing them and starting your rollout condition on them in turn one in the first place. So that allows you to sort of like both do some system optimization as well as just use off policy data really well as well in the first place. So you can do shorter on policy rollouts, much more efficient, and you can enable some kind of off policy RL, which usually you don't see with LLMs with this kind of an approach. So this sort of thing really worked well. So if you have sort of a 2 epoch training with an offline cache, you can do really well compared to like which is the blue line compared to sort of the orange line, which is purely online training. Or if you just do 1 epoch of purely online training, even that's the green line. So clearly having an offline cache really helps you overall in this case. Okay, so just to show you some quick results, and that's sort of the end of my talk after that. So we find it really substantially improves on the performance of the base model when you use the reasoning cache and many other open models. So we looked at it on some saturated LLM benchmarks. So in the area of LLMs, there's a lot of concern around how many of the base models that you see right now are kind of overfitted on the kind of test benchmarks people want to train on, because in theory, there's a lot of incentive for companies and big model players to actually show better numbers on benchmarks, which often means that there's a lot of similar type of training that goes into training, and that makes some of these observations a bit confounded. So we tried it on a saturated benchmark. So this work is still being done. So AMA 2025 came out in May or June 2025, which is much kind of technically speaking like a bit older. So we tried there. Our method did actually still do well compared to sort of just like taking the base model and just letting it run for longer with some kind of an inference algorithm. We did underperform though, like a lot of the other models that were released by industry, like models like Polaris and Qwen 3.4b Thinking, which are two models that some big players have released. But what we found was that on the newer benchmark, which came out during the course of our research, which is the HMMT benchmark from November 2025, we find that we do better than the base model like you saw on the left plot, but also better than many of these Polaris and Qwen 3.4b Thinking models. So this benchmark has questions that were not seen during training altogether for the base model, and so we can do much better than the base model. So this is kind of like a nice result that shows that we are not overfitting in some weird ways to sort of prior competitions or prior test benchmarks that we might care about. We also find that you can actually keep on increasing the number of tokens. So like, you can think for up to about 500,000 tokens, and you can keep on improving performance as you see on this plot, whereas like a very capable model at the same size saturates much earlier. And so there's a big gap. And we also sort of tried this on IMO problems, which have a final answer. And we again find that compared to sort of the base model, we do improve performance as we think for longer. And compared to many other existing models, including Polaris and Qwen 3.4b Thinking, we are much better as well. So that's kind of quite nice because these problems are really challenging. These are more IMO level questions which have a final answer in the first place. And also this benchmark was released again in like November or December. So it's also a relatively new benchmark. We also get some nice transfer from math to science. So you see that we always train our models on math problems. But now this general skill of like being able to summarize information and being able to like continue from there on actually does give you a lot more benefit on science benchmarks. So this Frontier Science is a benchmark from OpenAI, which was released in December. It has like no math questions, only chemistry, physics, and biology questions. Like an example set of questions is shown on the left. And you find it again, compared to the base model, the trained model actually gives you a lot better boost. Both in terms of absolute numbers, but also the gain keeps on increasing as you end up running the model for longer as well. So these exploration strategies at test time where you can like condition on summaries to do interesting stuff does actually generalize, even though the domain is very different, which is kind of like a very interesting result for test time exploration. So yeah, I think that's basically what I have here. So the main kind of takeaway from this part of the talk is to think about how can we use the ideas that, or how can we use priors that exist in these base language models to build recipes for RL, such that now when you run the model for longer on much harder problems, you can kind of learn to do very meaningful stuff, although you have never trained at that level, of problems at that output length. And you can do so by doing curriculum. You can do so by generating this kind of iterative summarization, generation type of thing that I talked about in this reasoning cache work. And all this allows us to scale these methods to a lot higher token budgets than what we can uh, train on in the first place, or actually even train on our training data. So that's quite interesting because this is really the kind of form of transfer we would expect from generalist models that we are seeing here. So yeah, that's basically it. I'm happy to take any questions. And this is work done by some amazing students at CMU and some of our collaborators at Stanford. And all the papers that I talked about or many of them are out on archive, and some of them are at least in the form of blog post available. So you should go and check them out. And yeah, thank you so much for listening. Happy to take any questions.
First, let's thank the speaker. Thanks, Viral, for this great talk.
Yeah.
So Aviral, actually we are running out of time. The next speaker is actually already ready. Okay, so maybe we have time for one question, and maybe we can send our questions perhaps by email to Aviral maybe after the talk. Is that okay? So is there someone wants to ask a question?
Thanks for the excellent talk. I have two questions. One is, so when you speak of exploration, the first thing that comes to mind is, let's say, things like Montezuma's Revenge, where curiosity-driven approaches or intrinsic motivation has been the way to attack those problems. Second thread is something like, let's say, goal-conditioned RL, learning from play. So can you speak to maybe how your methods align with or are different from those approaches? The second question is, you briefly touched upon offline RL. So given that these problems need more of policy optimization based approaches as compared to,
I lost you, I think.
Hello, can you hear me now? Hello.
Yeah, I lost you at offline RL.
Yeah. So given that offline RL methods generally are in the value based side, right? So they think about the queue overestimation problem and then they deal with that. Do those ideas also translate to this setting, or do you need some new machinery for the policy optimization kind of approaches? Thanks.
Yeah, this is a good question. So just to answer the second question first. So traditionally speaking, in off-policy RL or offline RL, there are two main questions, I think. The first question is the question of coverage or policy optimization, where you kind of need to be able to cover the right space of actions and states. And if you don't, then you cannot really do much about it. And in these sorts of problems where there's no multiple environment, there's no environment interaction, you're given a prompt, you're going to produce a trace, and you can do that as like an action or everything that comes from your base model altogether. You're going to get a reward. So here there's no notion of an environment. I think of queue functions as basically something that allow you to summarize the expected reward you're going to get in the environment, although you're not allowed to run environment interactions in the first place. But within the course of, let's say, at a given state, if I just wanted to find the best action, in traditional RL, I can run and I can sample multiple actions and maximize my queue function. So the way to think about this LLM setting would be that here you don't really have an environment. It's just one step of interaction. And so within that step, I'm going to try many different actions. And that's why you see a lot of these policy optimization questions come in. And I'm going to be able to maximize the reward condition on them. The reward function is known to me, so that's technically my queue function as well. And so I don't need to learn a value function in the first place because I have the reward function and I can just optimize actions right now. Now, it turns out that a lot of insights on policy optimization from offline RL literature do actually transfer here too. So a lot of the stuff, so if you imagine if you have a very large action space, turns out that the thing that works well in offline RL is the approach of sampling actions from your policy and or basically doing this mode seeking style policy optimization objective as opposed to trying to do a likelihood based policy optimization objective. And that does seem to still work well here. So in fact, if you do this SFT style approach that I was talking about earlier, you don't get a lot of benefits. It just does not help you solve hard questions. So that does transfer. But the queue function is not really present because the problem structure does not require you to learn a queue function. So that's the second question. The first question about curiosity-driven approaches and so on. So in a way, you can think about, so curiosity, the way it's defined in Montezuma's Revenge, for example, or usually it's defined, it often thinks about curiosity about some kind of prediction error, for example. Am I able to predict something? Do I have consistent beliefs about what's going to happen in the environment and so on? Again, here, there's no notion of an environment. It's only the stuff that the model is producing, at which point it's very similar to sort of just some notion of coverage over possible actions. which I guess we did benchmark. For example, we tried entropy, and that didn't seem to work. It's the most stable way of getting some notion of coverage. There is some work actually on implementing some ideas like novelty-based bonuses more precisely, like 1 over square root of n style bonuses precisely. But then again, the point is novelty over what object, or density over what object. You can do it over likelihood of the whole sequence, at which point it's the same as entropy that we did. You can do it over likelihood over some intermediate steps or responses or something else, at which point it becomes a bit more finicky because it's unclear how do you even measure density or likelihood or count of that kind of an object in the first place. So there is some work on it. I am not very optimistic personally about a lot of that directions, but I have not seen a very strong result on them either. So I do think that like we didn't compare to those exact things, but it doesn't seem like a very promising direction either. So that's what it is at. So I think it's really about like covering the action space or covering the possible things that my model can produce. And the best analog of a lot of these methods was just entropy in a way. So yeah.
Thanks, Viral.
Yeah. Does this answer your questions?
Yeah. Okay. So unfortunately, we are at the end of this talk. So thanks a lot once again, Aviral. I think it was a great talk. I think all of us benefited with some of the state-of-the-art algorithms that you and your students are designing. Okay. So there's a small change in schedule. So instead of us having a coffee break at 10, we will now have the coffee break 30 minutes from now. Okay. And in this next 30 minutes or so, we will have Professor Furong Huang giving us her insights on her work titled From Perception to Action, World Model Learning for Generalist Agents. So here is a quick brief about Professor Furong Huang. So Professor Huang is an associate professor of computer science at the University of Maryland and a visiting research scholar at Capital One. Her research focuses on trustworthy machine learning, sequential decision making, and foundation models for perception and control. She has made foundational contributions to world model learning, alignment of generative agents, and robustness in vision language systems. Dr. Huang's recent work explores how agents can implicitly or symbolically construct internal models of the world to support generalization, planning, and exploration. Her research has been recognized by multiple Best Paper Awards and supported by DARPA, NSF, ONR, AFOSR, and industry partners. Professor Huang, if you can hear us, you can go ahead and start talking about your work. Thanks once again for agreeing to be, talking about your work in this workshop.
It was my pleasure. Thank you so much for the introduction, and thank you for having me. Sorry about the scheduling issue a couple of days ago, and I'm happy to share some of the recent work that's happening in my lab, focusing on learning generalist agents specifically for robotics. So there is a lot of things that's foundationally related to reinforcement learning, but we're gonna talk more about world models today. Okay, so what actually makes good foundation models for robotics? I guess there is a lot of vision about how we can have generalist robots that's going to do all the tedious work for humans. But what would make a good foundation model? I made a wish list. I think there is definitely a requirement for versatility and generalizability and resilience. So in terms of versatility, definitely having being able to have adaptability to downstream tasks of diversity and specific algorithms of different kinds is very challenging. So the question is really, do we have enough data, right? So in terms of generalizability, I sort of wanted to focus on unseen tasks and domains, and I sort of also wanted to ask the question of, is next token prediction all you need? In fact, a lot of people believe that next token prediction is all you need to training a foundation models, but what about for robotics? Now, in terms of resilience, one of the things that I care a lot about is training data quality. So NLP, large language models, has been really successful because we're able to do data curation from the text data from the entire internet. But data curation for robotics is very expensive and it's always been the bottleneck. So we wanted to ask the question, is it possible to utilize lower quality training data? And in that case, is scaling up all you need? So I'm gonna answer these questions throughout the talk, but I want to start with saying that, even the very successful foundation models we're familiar with, there is this data inefficiency problem. We're not really efficiently using all the tokens that these models have been trained. For example, taking Llama 2 as an example, which was trained on 1.4 trillion tokens, arguably 3,000 or 4,000 times more than a human has possibly verbally exchanged at age of 50. So, but if you think about how efficient that is, basically is a really inefficient learning that the models are doing. So will we ever run out of data? Indeed, if you think about the compute that we are actually scaling up, right? We keep scaling them up because we have better hardware, we have better algorithms, we have larger clusters, but the data is not. In fact, we still have just one public internet, and the internet is the fossil fuel of the large language model. It's finite, is increasingly minded. So pre-training at internet scale is really hitting a data wall. And if you look at this training plot here, you can see that as you increase the number of tokens, the training loss is still not saturated yet. And you're still at a regime that more tokens will be so much more helpful for training the model. So as we know, pre-training is going to plateau, and progress must come from new data sources, new objectives, and continual learning or interactive learning. Well, so will we ever run out of data? If you look at this very interesting table that I'm showing here, if you think about the number of training tokens as used in recent large language models, let's use Llama 3 as one Llama, then GPT-4 arguably is using 0.5 llamas. But if you look at all the possible data that's out there, for example, the fine web is exactly at one llama. And the very high quality non-English web data is also at one llama here. Some people may argue that this is exactly the tipping point where we are going to run out of data. But maybe there is a lot of argument about some other data sources, but there are a lot of concerns about the privacy or legitimate use of this data. So still, I think we are really indeed at a tipping point where we're running out of data. Well, so when it comes to robotics, this problem is actually more pronounced. If you consider, this usual data collection in robotics is teleoperated, and doing some kind of corrective feedback is the major way of how we collect data, and we are bounded by human time, because you have to actually use humans to collect those data. It's not autonomous. It's not some parallel programming that you can use, right? You can use a larger team size, but it's basically fundamentally bounded by human time, by attention, and by safety concerns, and including hardware failures and just like physical boundaries that you have to respect. Now, as I said, robotics is human field, doesn't really scale. It's smaller than 24 hours of supervision, even if you don't go to sleep per day, right? Per robot and per person. Now, considering all the cross embodiment, as I'm showing in this slide here, that the robots could come in so many different shapes, different embodiments, different environment, different tasks, then this cross-embodiment learning is really making it worse in terms of the diversity. So the data efficiency problem is even more exaggerated. We're still in a small data regime for robotics, very counterintuitively. Although we've been collecting all these data for training these foundation models, for robotics, there are so many variations. So we are in a small data regime. Well, how do we deal with this, right? So we think about this real robot teleoperated data that's really scarce, very expensive, high quality, as I'm showing you here. People who have worked on it must have very much resonated with how painful it is to collect those data. But you would imagine that if we don't have to teleoperate the data, but we can have some controlled in-lab human data, which is essentially the humans, mimicking the embodiment themselves to do tasks in a way so that there is a lot of resemblance or a lot of similarity between the human doing the thing and the robot actually doing the thing. So, it will require you to hire some data annotators doing the task and, make videos of those human doing that. And this is still in lab controlled, right? It still requires human doing the task, but it's so much easier than teleoperating the data from the machine, right? It's still pretty expensive, but it's good quality, not as high quality as what you would do in terms of actually teleoperating the robot, but it's less expert demanding. You could hire mechanic Turks, or you could train people who are not experts to do these tasks in a very quality controlled way. Now, then you would also imagine that there is this in the wild human data that is very large quantity, just like YouTube videos or egocentric views or third person view of humans doing things, all these motions. It doesn't even have to be human, could be machines, could be different embodiment, is essentially in the wild data that is very large quantity but very low quality, just because there is no tracking of the action at all, and the variation of the task in the background is very, very exaggerated. So overall, you see this data pyramid where, from the top, you have this very high quality teleoperated data. In the middle, you can have some controlled in lab human data. And then bottom down here with very large quantity, you can have in the wild human data. So now what does this enlighten us, right? What can we do with this like small data regime and robotics? We really hope that we could utilize in the wild data. But going back to foundation models, let's take a look at all the questions we've asked at the beginning of this talk, right? So we have this data collected from diverse tasks and domains, and we train foundation model, we do forward pass, we have a training objective function, and we do backward pass. And, in large language models or variants of large language models, you often see like next token prediction, the pre-training objective. So the real question is that really what we should be doing? Now think about robotics, right? Usually you would get an image or, multiple images, but let's just be simple. You get an image as a perception, you go through an encoder to get an embedding of this observation. You take an action, to the environment, and then you could imagine that you wanted to understand, you wanted to make a decision. What is the action that you have to take, right? That decision can actually be played by if you have access to a world model that represents the world that you are interacting with. So now if you have that world model, what you can potentially do is that you can imagine under that action and under that observation, what is the next state? And you could do that again and again to roll out the entire trajectory to understand what that trajectory will lead to and what's the reward of that trajectory. So that's the power of the reward model. The world model that is able to allow you to imagine what's going to happen in the future under this action. So you can plan ahead through imaginary rollouts. Well, this is nothing, unfamiliar to, I guess, the audience here. Is just model-based reinforcement learning, really, right? Well, specifically, I think a lot of people believe that latent world model is really useful here because it would reduce computation and do every rollout and planning in the latent space. So the trajectory, the training objective should be essentially something that would help you to learn a good latent world model. And, instead of like doing next token prediction, what would happen if you end up like having this training objective in learning such a foundation model? Well, in fact, if you look at this, implicit latent world model I'm talking about here, you're not necessarily actually learning a world model, but you are trying to incorporate this world model learning into your objective function through modifying of your objective function. What will happen is that you hope that objective function would predict the next state given this current state and the current action, right? This is a simplification of it, but what we actually end up doing to examine how useful this world model is this work called TACKLE. It's a temporal latent action driven contrastive loss. What we end up doing is the following. So say that you're at a state, ST, right? You go through the state encoder. Your goal is to learn the state encoder. Okay, but you have some initialization of that state encoder. You go through it, learn a latent representation of it, ZT. But then what you do is you're gonna actually collect the trajectory from your replay buffer, which essentially gives you a sequence of actions, AT through AT plus K minus 1. So a sequence of K actions. Okay, so given that sequence of K actions, of course, you could also go through some action encoder. This is not very important, but at the end of the day, you hope that it would be able to predict the state at T plus K. Well, actually, more precisely, is the latent state going through that latent state encoder. Well, what we end up doing is we used a contrastive loss to make sure that this prediction is good and that we don't run into the weird issues if we simply just do simple like similarity scores. So contrastive loss is empirically proven to be very good. But what we end up doing here is essentially predicting observation latent K steps into the future using this contrastive loss. So if we have to, if we incorporate this loss into the learning, what would happen? So this is what happens. Essentially, you can see a significant performance boost compared with all the existing model-free and model-based reinforcement learning. And you may argue that this is not really a foundation model yet, right? You can see like a really good sample efficiency and performance, but it's not really a foundation model yet. Then we ended up doing something actually as a foundation model. In fact, there is a limitation of the tackle, which essentially is like the large batch size is really required for every single task. And you can see that when the batch size goes up, it's the reward gaining, it's going up. But if you have a small batch size, which means that it's going to be very expensive, right? So what we end up doing is from tackle, we realize that this contrastive loss can be made more scalable by being more smart about how to select the negative example in that contrastive loss. So instead of selecting all the other examples as a negative example, we end up doing something really smart by choosing a negative example that is really hard, that is really close to the actual positive example. So, it's basically in the small neighborhood of this positive example, we can do a random sample. So you can select one negative example, but it's a really hard and challenging negative example. Basically, it's very informative. And with that, this is being able to scale up. And we ended up building real foundation models out of this tackle loss, this, premium tackle loss. So you can see, this foundation model allows us to generalize from seen to unseen, from simple to harder, and from shorter horizon to long horizon tasks. I'm not showing you all the plots here today, but if you're interested, feel free to check the paper. I'm just trying to show you like a big picture concept here. So now we talked about data efficiency, but I still think that compute is something that we definitely wanted to reuse, because if you don't reuse the compute, you're also wasting the data that you've been using for training the model, as well as just the compute you've used for training the model. Now we know that the foundation models are so powerful, like vision language models, VLMs, are able to do perception in the wild. Then the real natural question to ask: can we infuse robotics capability into this VLMs so that you can have like a foundation model for robots, that's also being able to do very strong perception in the wild, but also very strong robotics planning. But how do you reuse data in this situation, right? So this is basically a recent work we've been doing, which is built on top of a GR00T N1 model, or you could imagine it could also be built on top of a Pi0 model, or Pi005 or Pi006 model. That's been like the recent state-of-the-art vision language action models. So what does a vision language action model architecture look like? It is very much resembling like, a transformer architecture, but with a variant. So starting with like image observation of the robot, or some language instruction as well, right? So pick up the industry object, then place it in yellow bin, something like that. So you first, go through some encoder, get image tokens, language instructions, same, tokenize them. So you get image tokens and text tokens. Then you go through a vision language model, right? This could be a pre-trained vision language model. For example, these vision language model, that's very powerful there. Then you could have also robot state, right? That becomes, through some encoder becomes some like also tokens, orange tokens. Then on top of that, as a head of action prediction, you use a diffusion transformer to predict the action. So it becomes a denoising process where you sample from noise as the action tokens on the left, and then you denoise it into the actual actions. In the training process, you're going to use ground truth actions as expert policy data, right? So do imitation learning and learn this diffusion transformer as the policy head on top of this vision language model. Well, this has proven to be pretty useful, right? Pretty successful in these foundation models. But one thing that is lacking is that capability of building this imaginary rollout, the world modeling, the capability of being able to do planning of the future and then re-examine whether this action is good in the future long term. So we end up adding this world modeling to the foundation model. And you can see that this process is really trying to reuse compute, reuse data, because we're still maintaining the vision language model and the diffusion transformer. You may have to retrain this, but it's a very light training compared with retrain the vision language model from scratch. Okay, so yeah, is there a question or something? Okay. So what is it really doing? So again, so you have this, before this, I think we've already talked about it, how, noised actions are gonna go through a denoising process through this DIT, and you get an action predicted. So we're gonna use a flow matching loss for this, and a lot of the, state-of-the-art architecture are just using flow matching loss. And then what do we end up doing as this world modeling is essentially to predict the future observation. So you can see that, through some alignment objective functions, which we basically call the future latent alignment loss, we're able to modify the objective by adding this future latent alignment loss and do the training. And this is what happens. So you can see we get state-of-the-art multitask imitation learning performance for humanoid tabletop tasks. You can see significant improvement compared with all the state-of-the-art, and including the foundation models. Okay. What's also interesting, you can see that Flare, which is the algorithm's name after we do the world modeling, it is really performing very well for these tasks. And you can see that what we're showing here is actually 1 times speed, so there is no speed up at all, which is very impressive. But what's even more interesting, as I talked about this data pyramid, if you remember a few slides back, that this kind of human egocentric data, which is cheap to collect, which lies at the second tier of my data pyramid, it is really useful for boosting the performance of this model. Compared with robotics teleoperation data, right, which is much more expensive, as we talked about earlier. Now, if you do this joint training without telling you all the details, it end up like getting a huge performance boost. And I think part of the reason is because you are able to use the human data to boost the volume of the data so that you could make the learning much more efficient. This is what happens when you have the human ego video co-trained versus not. You can see the performance is really improved significantly when you have this human ego video data as a co-training. Now, so going back to this data pyramid, right, we talked about how controlled in-lab human data can really be helpful, but what we really want going forward is in the wild human data, say like all YouTube videos, all the data that is motion related can be utilized for training. That would be great. That's going to be like the fuel web scale kind of training for robotics, right? If that's possible, then that is really going to make learning much better. So going back to what we've talked about, right? We talked about latent world modeling. As we talked about earlier, right? So this is a prediction of the future given the current state and action. But it was on latent. It was not something that you can actually interpret or feel, whether this representation is good or bad. But robotics is really about doing something. It's about motion, right? So then we realized that with all these tasks there, maybe there is a interpretable symbolic representation space, maybe a key point based one, maybe a trace based one that is, annotating the trajectory of the movement could be a really good symbolic representation space. And is that true? In fact, if you imagine that, robots observe the environment by taking pictures, if you go through this kind of trajectory extraction so that you get the traces of the movement as a symbolic representation space, then it ended up being a possible symbolic representation. And on top of that symbolic representation, you could also do world model prediction. You could use the current symbolic representation of the current state and together with an action predict the future symbolic representation of that next state. How does this work? So we started to test this idea by improving existing VLAs by a very simple thing. So you could imagine that given a trajectory of a task, starting from an initial state to a final state, you could find some key points, multi-key point tracking using some existing algorithms. And then on top of these key points, you can see you could try to generate a visual trace from these key points. Okay? If you end up doing that, then you will get something like this, a visual trace prompting laid on top of this original image. Now, if you put both the original image and the visual trace prompted image, which have this visual trace overlaid, and put it into just a VLA, you don't train anything. It's just basically a prompting, a different prompting. Then what you end up doing is that you could just improve the performance because of the visual traces of the historical trace of the current state. And that really made us think that if simply just providing the historical trace is so helpful, can we actually do a trace world model prediction? And so this is basically the idea of TraceGen. I don't know how much time I have, but I think it is really interesting to show you this video here.
Teaching a robot task can be surprisingly simple. Just record a video. Our system, TraceGen, can extract full 3D motion directly from handheld, uncalibrated phone videos, even when the videos are from humans. With just 5 short handheld videos, TraceGen can be quickly fine-tuned to adapt to a new robot and a new environment, learning the demonstrated skill directly from video. This lets the robot handle a wide range of skills, thanks to the strong motion prior learned during pre-training. And it doesn't have to stop there. These skills can also be linked together, allowing the robot to perform longer, multi-step behaviors when needed. In this way, TraceGen turns cross-embodiment motion, including everyday human videos, into reusable 3D motion primitives. All you need is a phone, a few seconds of video, and a robot ready to learn.
Yeah, so this is basically like I think I'm losing my, wait a second. Okay. My slideshow, give me 1 second. Here, okay. So, so TraceGen essentially is a way of thinking like how to really scale robot learning. We talked about this pyramid, and we're essentially using this lowest web scale image, video data for training. How do we do this? Basic idea is a shared 3D trace space so that, we ended up providing a trace fort, which is a data engine pipeline to generate these traces from any video. and TraceGen, which is a world model on the trace symbolic representation. So it's a unified world model, a foundation world model that works for any future trace prediction. And that's it. So, such a simple idea. You end up we do a lot of engineering work for data engine. We used 123K videos, like a lot of observation trace language triplets. And then we trained our world model. And now, when you have a new environment, what we can do is, you just take a few demonstrations of a task with a handheld iPhone, shooting your partner doing some simple tasks. And then you can just throw it to TraceForge to convert it into a 3D trace annotation. And then just like warm up your TraceGen, and then the TraceGen will be able to do the job for you. So you can see that the performance is really impressive. If you see the figure on the left, NOAA Flow is actually like a video prediction world model that is state of the art. But if you look at the x-axis, which is the test time efficiency, of course, you want it to be as efficient as possible. So the larger, the more efficient. And on the y-axis is the success rate. So if you look at TraceGen, which is basically here, it is like 50 times more efficient than NOAA Flow compared with this kind of world modeling on video pixel space, because we're doing things in a much more efficient symbolic representation space. But also, we are much more successful compared with NOAA Flow, right? You can see a huge boost in terms of the success rate, in terms of like, being able to do the task out of the box. So we can, do very simple warm up. We can do human warm up. We can do robot warm up, and the performance is just really, really, impressive. So going back to this, we're still in a small data regime, given so many different variations. Given the last 5 minutes, I know I'm running out of time, but the last maybe 1 or 2 minutes, I just wanted to tell you that we've been trying to solve the small data problem by collecting data using the model itself. So how do you do that? Essentially through some exploration process. So we're using a large language model to do that, a vision large language model to build an agentic framework for doing it. Very simply, I just wanted to show you how we can do self-collection of the data. So it's like motivator from humans, like, human babies. We explore the physical environment. We have self-generated task goals. We have intrinsic innovation motivations and so on. But those are human guided, right? Well, actually, if you think about exploration RL, indeed, they are trying to do that, but unfortunately not very successfully, as you can see in these videos, right? So exploration RL is really, really nice, but it doesn't really work in a lot of real world situations. So we think about this, now that VLMs are so powerful, can we do something here? And basically what we're thinking is that VLMs are able to do object semantics, spatial relations, and, potential outcome understanding or prediction. Then with all these capabilities in the VLMs, can we have a VLM powered AI agent that is, utilizing these capabilities to do data collection autonomously and to do exploration autonomously, right? So that's the idea. Although, it seems like they have all these capabilities, but they're not physically grounded. They don't understand the actual physics of the world we live in. So that's why we have this IVE work, which essentially is a way of, grounding a VLM so that it's an agent that is understanding physics, but is also able to explore the environment in a very efficient manner to collect data. So here's how it works. So, imagine that you have these observations, and then you're going to generate a scene graph using your VLM. And VLM is pretty good at it because, has a very strong capability of perception and object detection in the wild. So given that, we'll have a memory system. And this memory system will essentially store the scene graph. But then together with the memory system, the large language model, the vision language model, is going to also do a job of explorer. It will act as an agent that is able to explore what are the possible actions I can do so that I can transit to a different scene graph. So if you ask this question to vision language models, it's usually actually very good at finding the novel actions that they can do to find or to make sure that the environment transit to a new state. Now, obviously, VLMs are not physically grounded. So that's why we have this verifier that can verify whether the suggestion is right or wrong. You know, if the suggestion is not right, then we provide a reason. If the suggestion is right, we're actually going to do it so that we can implement that action, implement that skill sequence, and we can achieve a new state and collect data. So that's about it. I don't think I have a lot of time. So you can see the results showing that it is really able to do very good job compared with exploration RL, compared with even the human exploration, that we're able to do very good job at exploring the new novel states. And also, if you consider some kind of downstream task using this data collected, you can see, you know, phenomenal performance. Without giving you all the details, I think I'm gonna stop right here to talk about the now and the future. So we talked about dealing with the small data problem using, you know, world modeling and in the wild behavior data. But I think, you know, there's also the future of like, you know, enhancing the brain of the VLM using some kind of spatial temporal reasoning capability enhancement, or enable this function and interactive aware reasoning capabilities. So overall, I think there is a very bright future that we can utilize, you know, these agentic frameworks, this kind of foundation models, smarter ways of utilizing data, and better objective functions to regulate the model to learn better from the very small amount of data. So yeah, I think that's all I wanted to talk about today. Thanks.
Thank you, Professor Huang. Let us first give a big round of applause.
Thank you.
I think we have time for one question. Does anyone have a good question? Okay, so maybe I'll try to pose one question. So you are looking at this world model idea, right? So at a high level, I understand that world model is like trying to figure out a simulator, right? So if you build a good simulator, are you still saying that we have small data? And also I wanted to know, do you sort of do like an online training of the simulator as well as you get more and more data? Can you elaborate a bit on that?
Yeah. That's a very good question. So we end up not building the explicit world model, which is something I do want to, you know, try to do. But, you know, right now is an implicit world modeling because it's all about using the training data, adding a regularization term, and that regularization term is really to minimize the world model prediction error. And there are some subtleties, such as, you know, you don't want it to do, you know, short-term prediction. You want it to do long-term prediction to, you know, make sure that the compounding error is smaller. But overall, is an implicit world modeling, very different from the explicit world modeling that people use, like, you know, video prediction models, or video generator models to do world model prediction. Actually, going back to, you know, the trace gen that I was showing you guys, you know, with the video, it was sort of like a explicit world model, but it's in the symbolic representation space. So, you know, in some sense, it is, you know, the trace gen model itself that we publish is meant to be serving as a foundation model for, you know, symbolic representation world modeling.
Thank you. So if you don't have any more questions, maybe we can thank the speaker one more time.
Thank you. Thank you again for this nice opportunity, and hope, you know, if there's any other questions, feel free to reach out to me.
Sure. Thank you. Okay, so we will now break out for coffee. Maybe we can reconvene at 11 a.m. Okay, thank you.
Thanks.
Introductions is an assistant professor in Department of EC at IISc, and prior to that she had postdoctoral stints at Georgia Tech and CMU. She got a PhD from TIFR and BTech from IIT Delhi. She's got multiple fellowships, Inspire Faculty Fellowship, Google PhD Fellowship, and Sarojini Damodaran Fellowship. And she was also selected as a rising star at the TCS for All workshop at Stock, which is a theoretical computer science venue. And her research interests are in applied probability and sequential decision making, which is also known as bandits, RL, and sequential hypothesis testing. Over to you, Shweta.
Thanks, Prashant, for the nice introduction, and thanks to the organizers for having me here. Thank you all for staying till the last day. So today I'll be talking about some recent work on concentration results for stochastic approximation in presence of Markovian noise. As we will see, there are many applications of this. But in this talk, we'll be focusing on stochastic approximation rather than reinforcement learning. Okay? Please feel free to stop me at any point whenever you have questions, any clarifying questions or otherwise. Please feel free to stop and ask questions as we go along. It's important to understand the setup before we move to the results. So yeah, just feel free to stop me at any point. Okay? So let's get started. So this is a joint work. It's an unpublished work. It's not yet on archive. So it's a very recent work. It's a joint work with my postdoc advisor Shiva Teja Magluri from Georgia Tech and another collaborator of ours, from Martin Zubeldia from University of Minnesota. So let's start by looking at some fixed point problems. Suppose we are given an operator or a function f bar which takes in a vector from Rd and outputs a vector in Rd. We are interested in finding a fixed point solution, which means a vector x star that satisfies this equation over here. Okay, that's what is called as fixed point. Then now consider the simple iterative scheme. By now you may have seen this multiple times, but just to fix some notation, let's go over it slowly. So consider the iterative scheme, which is the next iterate or the next estimate xk plus 1, that is f bar applied to the current iterate. Okay. So now if f bar is a contraction, meaning it satisfies something like this pictorially, that is it takes in two vectors x and y, and when you apply the function f bar, some notion of distance between them, it reduces. Okay, that's what a contraction means pictorially. So if the function f bar is a contraction, then Banach fixed point theorem says that this iterative scheme, this will converge to x star. It will in fact converge fast to x star. Okay, and formally this is what we mean by contraction, but the definition is not important. It's sufficient to keep this in mind. But now notice that this particular iterative scheme, this assumes that you have access to the function f bar exactly, which means if you have an oracle, if you query that oracle at x, you get f bar of x as output. But this may not always be true, right? What if you don't have access to exact f bar, but you only have a noisy access to f bar? Just for illustration, I am representing this as an additive noise. We will generalize this later on. Okay. So now the iterative scheme from the previous slide, that reduces to this over here. But it can be shown that this iterative scheme does not converge to x star. Okay. So a modified version of this, a generalized version of this was proposed by Robinson Munro in 1951, which said, okay, the previous scheme was evaluating, so the next estimate for the fixed point was just the evaluation of the function or the output of the oracle at the current estimate. Instead, let's generalize it. Let's take a convex combination of the current estimate and output of the noisy oracle. Yeah, where alpha k is the step size, the weight to the convex combination. We can rewrite this as the bottom equality here. It's an equality, nothing changed here. Now the question is, does this work? Does this iterative scheme work? This one did not work. If you set alpha k equal to 1, you recover the previous one. But for any general, so this is more general scheme than that. Now the natural question is, does the scheme work? And it has been long known that the asymptotic convergence of this iterative scheme at the bottom, Robbins-Munro iteration, asymptotic convergence of this has been known at least since 1990s. Yeah. In this talk, we will try to answer the question, how well does this work? So notice that these xk's, these iterations over here, the iterates over here, these are random variables because of presence of noise. So there are multiple ways to characterize how well or how fast these converge, right? We can talk about almost sure convergence. We can talk about convergence in moments or second moment, first moment. We can also talk about concentration. So in this talk, we will focus on the concentration properties. So if this were, for simplicity, let's just consider these are real numbers. And we will ask the question, what is the probability that the distance between xk and x star is greater than epsilon? Can we get a bound on this? Okay, we'll try to answer this question. Okay, so this is the broad outline of my talk. With this brief introduction about stochastic approximation, we'll try to see some motivations about it. We'll continue with the background a little bit more, and we'll see some connections to reinforcement learning. Then I'll introduce the formal setup that we consider in our work and our results, and I'll conclude with the proof sketch. Okay. So yeah, let's look at some examples why understanding the theoretical properties of stochastic approximation iterates is important. So recall, this is the stochastic approximation is used to solve this fixed point equation, solution of this fixed point equation, and this is these are the iterates that we consider. Now, in optimization, where the goal is to minimize a convex function, or the goal is to minimize a function, one typically proceeds by considering gradient of f equal to 0. Nothing changes if I multiply both the sides by minus eta and add x on both the sides. Yeah, so this thing is equivalent to solving this equation over here. Now, this can be, now if you define this as your f bar, this is nothing but solving for a fixed point. Okay? Now, if the function f that you consider, if that is smooth and strongly convex, one can show that for appropriate choice of eta, this function becomes a contraction. And the corresponding stochastic approximation iterate, if you write this for this particular choice of f bar, it reduces to stochastic gradient descent. Stochastic because you don't have access to gradient of f exactly, you have a noisy access to that. So that's the stochastic gradient descent. Okay? Moving ahead, so suppose you want to solve for a solution of this linear equation, ax equal to b. You want to solve for x that satisfies this. Yeah, we know a number of ways to do this. One is like just inverting the matrix. The other is Gaussian elimination. But what if you don't know a and b exactly? You only have noisy access to them. Yeah? So again, you can rewrite this equation. I did nothing but multiplied by eta on both the sides and added an identity x. Okay, so nothing changed over here. This is equivalent to this. Now you can see that this is again a fixed point equation. Now if the matrix A, if it satisfies certain properties, then you can again show that this is a contraction. By the way, so in the definition of contraction, there is a norm involved. We were talking about distances reducing after application of a function. For our purposes, the choice of norm doesn't matter. Any general, if you can show that f bar is contraction under some norm, our results hold in that case. Okay, but for simplicity, you can consider 2 norm. But 2 norm is simpler to handle. Yeah. Okay. Yeah. Right. So the conditions on eta as well as the matrix A. Yes, the choice of the step size is important. Yeah. Okay. So so again, this is a fixed point equation. You can write a linear stochastic approximation for it, the corresponding instantiation of that algorithm. Yeah. And so, okay, whatever we prove about, if we can prove anything about the iterates over here, if the conditions are satisfied, then all those guarantees extend to these setups. Yeah. So now our motivation was mainly coming from reinforcement learning, which is used for a large-scale sequential decision-making problem. And all of you are aware of the advances in reinforcement learning. In particular, like AlphaGo was able to beat the best human Go player in the world. Similarly, DeepMind's street navigation projects, or AlphaFold, was able for protein studying the protein folding structures, and OpenAI's robotic arms, to name a few. In this talk, I'll not dive into the reinforcement learning as such, but I'll just show where the connections to stochastic approximation come in briefly. You may have already seen that till now, but just to be on the same page. So in the reinforcement learning setup, there is an agent which interacts dynamically with the environment. So at each time, the environment is in state, let's say ST, And at time t, agent takes an action at according to some stationary policy, mu. And on doing so, the environment evolves to a new state st plus 1, and the agent observes a reward, which is a function of current state and action. Now, the ultimate goal of reinforcement learning is to find an optimal policy, optimal in some sense. But there is also a smaller goal, which is given a policy, evaluate how good that policy is. Yeah, this is called the policy evaluation problem, and the above, that's the control problem. You may be aware that, okay, so what is an optimal policy? Optimal policy is something that maximizes some function called Q star, okay? But it is well known that this function Q star that typically we are interested in, that satisfies certain fixed point equation. You may have heard of Bellman equations. Those are these fixed point equations, yeah? Similarly, if you are given a policy, the value function of the policy, that also satisfies another fixed point equation, yeah? Both of these are what are known as value functions, both in Bellman equations, yeah? Now, in reinforcement learning setup, again, we don't have access to these functions exactly. We only have access to the model through samples. So we don't have access to these functions exactly, which is why a lot of algorithms there are actually instantiations of what are called stochastic approximation algorithms, okay? Now notice that in the reinforcement learning setup, the samples, they follow Markovian, they have a Markovian dependence across time. From here you can see that, yeah, the next state depends on, so the evolution is Markovian. The state at time t plus 1 depends on the current state, or the reward at time t is a function of the current state of the Markov chain and action that we take. Yeah, but it's independent of the, like, given this information, it is independent of the past. So there is a Markovian dependence across time. It's not a IID sample. So it's important to study stochastic approximation in presence of Markovian noise. So in this talk, we will focus on stochastic approximation algorithms, where the underlying noise will follow a Markovian dependent structure. Okay, I'll introduce the exact noise structure in the next slide. But any questions before we proceed? Okay. Yeah, so with this brief overview, let's go into more detailed setup. So there are many moving pieces that will be there, so we'll spend a little time on the setup. Please feel free to stop me if there are any questions. Okay, so now we want to solve a fixed point x star that solves this equation over here, where f bar is an expected operator. Okay, I'll come to this. F bar is some expected operator. It's an average operator. Okay, so now the noisy operator that you have, it's a function of, so the one argument is the state space of an underlying Markov chain. So let's assume there is a finite state ergodic Markov chain with stationary distribution pi, and f is a function defined on the state space. And in addition, there is another additive noise. Okay, so there are two sources of noise. One is the underlying Markov chain, which is evolving over time, and then there is an additive noise. Okay. For the Markovian part, we assume that it's a finite state ergodic Markov chain, and it has a stationary distribution pi. And your average operator, that is actually the expected value of this thing, where the expectation is with respect to stationary distribution pi of the Markov chain. And we also assume that the additive noise is either IID or a martingale difference sequence. So, and in addition, it has mean 0. So the average operator is actually the expectation of this, where the expectation is with respect to stationary distribution and the noise of WK. So noise of WK cancels, and this is what remains. Okay? Okay. As a terminology, we will refer to this WK as additive noise, and the noise due to the Markov chain, that as multiplicative noise. It will become clear why that terminology, but that's what we'll refer to. Okay? So, okay, notice that the multiplicative noise, or this part, it's biased. So at each time, at time k, its mean is not, so the mean of the noisy operator minus the average operator, that's not 0. It's only 0 in the limit. Like at stationarity, this is 0, but for each k, it is not 0. That's one challenge that's typically there in the Markovian setup, because the noise at each time is not unbiased. Okay? Okay, now we can, with this noisy operator, we can instantiate our stochastic approximation algorithm as here. This is nothing but we just instantiated our stochastic approximation algorithm with this noisy operator, okay? Now, again, just for simplicity, recall we had this linear stochastic approximation, which was this. Now here, if AK and BK are random matrices, which can possibly be functions of the underlying Markov chain. Yeah, so this is just one example. A very useful example to keep in mind to get some intuition about the concentration results is the law of large number setting, which is if you instantiate this algorithm with alpha k equal to 1 by k, and let's say this operator is identically 0. So this vanishes, and let's start with x naught equal to 0, just start 0, original iterate is 0. Then you can show that the iterate at time k plus 1, it's nothing but empirical average of the additive noise. So very instructive example to keep in mind is this, just to make sense of the concentration results, because we know of concentration results in this setting. Yeah, okay. So let me remove that. So, okay, now that there are multiple moving pieces here, we'll need some assumptions. Without any assumptions, we cannot give any guarantees. So we need some assumptions. So let's state what assumptions we'll need. We'll relax some of these later on in the talk. So to start off, we assume that the additive noise is bounded. So we'll start off with the simplest setting, okay? We'll assume that the additive noise is bounded. So this is saying that the norm of Wk is bounded, or if it's a one-dimension thing, it says that, okay, Wk lies between minus B2 and B2. So there's a bounded support. Similarly, to start off, we will assume that the multiplicative noise is bounded, meaning the noisy operator minus the stationary or the average operator in the norm, this is bounded by A1 x plus B. So notice this does not ensure that the iterates are bounded, because this noise is still multiplied with the current iterate. So it's a so in this sense, it's a multiplicative noise. So this does not guarantee that the iterates are bounded, right? So even if this B is 0, let's say this is also 0. So at each time, xk is getting multiplied, right? So this noise is multiplying the current iterate. So the iterates are still allowed to blow up. Yeah, depends on A1. Okay? Okay. So yeah, to start off, we will have these two assumptions on the noise. Now coming to the operator, we assume that f bar is contraction with respect to some norm. It could be an arbitrary norm. And further, we need a little more assumption, which is that the noisy operator is uniformly Lipschitz. Okay, these assumptions are even required for getting weaker guarantees like mean square error convergence. So it's not surprising that we need them in getting concentration results. Mathematically, this is what we mean by contraction under the C norm, and this is the uniform Lipschitz property. Okay? Okay, so let's remove some of these things. So with these assumptions, one can prove that the noisy operator minus x star, it satisfies some bound. So this is like a pseudo contraction in some sense, okay? So with these properties, like we assume that f bar is a contraction and the noisy operator noise satisfies these conditions. So using triangle inequality, one can prove such an inequality. What this says is if d, this constant d is actually a function of the noise parameter here and the contraction parameter. So if that d, if that is less than 1, then what this says is your noisy operator is an approximate pseudo contraction. So think of pseudo contraction as contraction. It's just some generalization of contraction, but we are comparing it to x star rather than f of x star, yeah, rather than f of x. So we are considering distance of the noisy operator from the fixed point. So if d is less than 1, this is almost like a contraction, except that we also have this additive term. So it's an approximate pseudo contraction. Xk's are, sorry, xk, oh, yeah, sorry, this has to be x, that's a typo, thanks. This has to be an x, okay? If d is 1, then it's non-expansive operator, and if d is greater than 1, it's expansive with positive probability. Right? This is an almost sure statement. If d is greater than 1, it's an expansive operator with positive probability. Okay? So our concentration results will depend on how this d varies. Like, so, okay, just to point out, d depends on the variance of the multiplicative noise or the bound here on the multiplicative noise and the contraction factor. If it's it's very strongly contractive and this variance is very small, it's likely that the overall noisy operator is itself a contraction, and that's an easy setting. Instead, if the noise variance is large, even if the contraction is strong, it is possible that the noisy operator is actually expansive, and that's a hard setting. Okay? Intuitively, it should make sense. If the noise that you are multiplying with, if that has a large variance, it is possible that the noisy operator takes your iterate very far away, and it's not a contraction. Yeah? So essentially, this D parameter, or the summation of these two, determines the tails of the iterates, will determine the tails of the iterates. Okay? Okay. So let's remove what we don't need, and let's see. So the question that we'll try to answer is, can we get a bound of this form? Maybe not exactly of this form, but something like this. Can we get some exponential concentration? Just to, so recall law of large number setting. Okay, I think I'll come to that later. So we'll consider step sizes, or general step sizes of the form alpha upon k to the z. We won't restrict to z equal to 1. We'll consider 1 by k to the z step sizes for z lying between 0 and 1. And just to, so the above the question that we asked, that.
Quick question.
Yeah.
Why do you want, in the previous slide, why do you want exponential c epsilon and not epsilon square?
Oh yeah, so great question. So so notice this is squared error. So if you recall, law of large number setting said that xk's are empirical averages. Let's say x star is 0. This is saying empirical average square greater than epsilon by k. So this is actually sub-Gaussian tail. That's what I want to point out.
Fine.
Because this is a squared error, it's sub-exponential.
Yeah, because you assume boundedness, so
Right.
we are in sub-Gaussian region.
Right. So you cannot have better tails, because this is a sub-Gaussian tail actually.
I didn't notice the square. Thanks.
Yeah, there is a squared error. Thanks for that question. Yeah. So this bound is on squared error. So just to recall, if you are in the law of large number setting, xk is empirical averages. Let's say x star is 0. In that case, it will be 0. And let's say we are in one dimension. Then this is saying square of empirical averages greater than something is smaller than something. But IID is a special case of Markov chain. And in that setting, at least from Hovding's inequality, we know that so empirical averages, square of empirical averages can be like sub-exponential. If empirical averages are sub-Gaussian, square of empirical averages are sub-exponential. And that's what this is asking. Yeah? So this bound is on square of empirical averages. Yeah? Okay? Okay. Any other questions? Okay, great. So yeah, just we can invert that bound and ask for, this may be more familiar to some of you, like square of empirical averages, or empirical averages greater than square root log 1 by delta upon k. That is at most delta. That's what Hovdings give us. Yeah, we are asking for more general stochastic approximation iterates. Can we prove such a result? Okay? Okay. So let's see what the challenges would be in proving such a result. First, as we observed, so we consider multiplicative noise, which allows for the D parameter that we had to be greater than 1, which means the iterates, so the operators can be expansive with positive probability. Second, so mostly in the literature, there are some works which consider exponential, which consider like concentration results, including some people in the audience have some nice results in this direction. But generally, in the stochastic approximation world, most of the literature focuses on mean square error convergence. And typically, like when you prove a mean square error bound, linearity of expectation helps. But right now, if you recall, in proving concentration results from the proof of Chernoff bound, you may recall that you need to take an exponent and then take bound on moment generating functions. So you need to go to the exponent. So yeah. So linearity of expectation no longer holds, and that introduces challenges here. Yeah. Thirdly, we consider also Markovian noise, which introduces bias at each time. So we no longer have zero mean random variables, let alone like IID-ness. So we no longer have zero mean random variables. So we need some clever techniques to handle this as well. I'll introduce what the techniques are. Finally, we consider general step sizes, which is, we consider step sizes of the form 1 by k to the z, where z lies between 0 and 1. one step size of the form 1 by k is easy to handle, but getting to 1 by k to the z for z less than 1, that's a very challenging part. Okay. Yeah, in the last part, yeah, sorry.
Why do you say z less than 1 is challenging?
Because it's very expansive. The operator is very expansive. The usual proof techniques, at least, that requires some novel ideas to handle for z less than 1.
Okay.
Okay. Finally, in the last part of the talk, we'll actually relax the bounded additive noise assumption. We'll relax it to arbitrary noise. Okay. But this will be the last part of the talk where moment generating function itself doesn't exist. So how do we prove concentration there? Okay. Okay, so let's see what the previous works. So I'll only refer to the very relevant paper. There are many other works as well, but I'll only refer to the very relevant paper to our papers to our work. So in 2025, Chen et al. They proved concentration results, similar concentration results, when under the assumption that the noise are IID. They do not consider Markovian noise. They consider IID noise, so and they get concentration results that handle. So their technique handles the first 2 points. Okay. But they do not. Their technique fails in presence of Markovian noise. Further, they cannot handle general step sizes. The proof technique breaks. In fact, you cannot extend that. And of course, they cannot handle the general additive noise that we will see in the third part of the talk. Okay. Very recently, Kuan et al., they also consider Markovian noise. So they handle the multiplicative noise. They get exponential tail bounds in presence of Markovian noise. But the rate of convergence is slow. So here, by rate of convergence, I mean this parameter here. Yeah, if you have 1 by k step size, you should have 1 by k over here. So the rate of convergence that they have, that is slower. They don't get the optimal rates of convergence. Further, again, they cannot handle these two generalizations. They cannot get concentrations for general step sizes, neither for general additive noise. Yeah, question.
So can you just elaborate, if you have an expansive setup, right, why should you even have concentration? It's not clear to me. Even convergence is not clear to me.
So expansion is for the, so recall the operator is still, average operator is still contractive. Expansion is only for the noisy operator.
But that is what matters, right?
So
because
yeah,
unless you are saying asymptotically this d becomes less than 1, I'm not sure why you should.
Oh, there is no asymptotic statement in D. D is a deterministic quantity. It was just an addition of like the contraction factor and the noise variance. So as long as your noise is bounded or you have a contraction, you can still show convergence. In fact, we can prove concentration results. So we still need, like, D may be greater than 1, but we still need the underlying operator, average operator, to be contractive.
Okay. I mean, so then I guess the hope is that the noisy operator eventually goes close to the, this averaged operator, right? And that's how the, maybe the, see, you had that gamma C plus the A thing, right? Yeah. So the gamma C plus that A thing, perhaps that additional part goes to 0 as, your steps, I mean, your iteration becomes larger and larger. That somehow should, come together to ensure that eventually the, there is no expansion.
Right. Okay. So the assumptions that I stated, those are sufficient to ensure that there exists a like Lyapunov function. The convergence is guaranteed. So yeah, we don't need any additional assumptions. I guess the Lipschitzness, uniform Lipschitzness of the noisy operator, that's where that's crucial for existence of. Yeah, in addition to this D greater than or less than condition, we also had this additional condition of noisy operator being uniformly Lipschitz. Yeah, together these ensure that you have convergence. No, so we will prove the concentration result. We will prove a bound of this form. Or like maybe not exactly this, the tail may be heavier depending on the noise. But we'll prove a bound of this form, and notice from here you can derive mean square error bounds, or yeah, you can integrate this out and derive the mean square error bounds. Yeah? Yeah. No, so remember, even if the noise is IID, XKs are not IID because there is this dependence. There is a dependency over here.
So by IID noise, are you referring to the multiplicative noise or the?
So it doesn't matter, right? Doesn't matter whether you have additive or multiplicative noise. Remember this, even if this is IID, and let's say there is no Markov chain, that's a purely additive IID setting, right? Even then, xk plus 1 is dependent on xk. So the iterates xk's are not dependent. But yeah, like that actually doesn't matter. If you go to the exponent, if you do the Chernoff trick, e to the theta xk, there is no linearity of expectation that you can use in exponent, right? There is no linear structure. So that's what I meant by linearity.
Okay, thank you.
Yeah, thanks. Okay. Okay, so let me present our results. So for the case of z equal to 1, which is 1 by k step sizes, so step sizes of this form is z equal to 1, we can show that if d is less than 1, meaning the noisy operator is a pseudo contraction, we can get a sub-Gaussian tail. We can get exactly this kind of bound. Yeah? If d is greater than 1, we cannot get sub-Gaussian tail. We get slightly heavier tails. So the way to see this is there is a log 1 by delta to the power m. You don't get m equal to 1. This log 1 by delta, so m is something that depends on d, as you would expect. The more expansive the operator is, the heavier tails you get over here. Okay? The exact form of m is not important, but just notice it depends on d, or d minus 1 in that sense. Like d minus 1 is the contraction or expansion parameter. And yeah, so for d less than equal to 1, we always get sub-Gaussian tail. And remember, like just, it's always helpful to keep this law of large number setting in your mind. So yeah, we are in the bounded noise setting, and if d is less than 1, you cannot do better than this. Even in IID setting, you cannot do better than this. So here, you should definitely not be able to do better than this. And for d greater than 1, we get what is called sub-Weibulian tail. It's lighter than a polynomial. Like it's not decaying 1 by x. It's like e to the power minus x to the power something, 0.5 maybe, something like that. So, or in the inverted form, the concentration result looks like this. And we can also show that even this bound is tight. You cannot improve on this in terms of dependence on delta and k. Okay, so this is the tightest that you can achieve. Yeah.
How do you set alpha?
Yeah, so right now it's dependent, so I'll come to that. Right now it's dependent on, so it has to be small enough in order to, yeah, it needs to be small enough dependent on some problem parameters. As long as it's small enough, you get this concentration. Right, yeah. So the usual conditions that you need for convergence, the same conditions. For mean square error bounds to hold, the same, yeah. Right, yes, yes. Yes, I'll come to that, yes, thanks.
I mean, just to build upon what he said, see, typically the choice of alpha depends on problem parameters when your z is 1. But somehow, the way you have written it, at least it gives me the impression, oh, here you are with z equals 1.
This is for z equal to 1. Okay, this is z equal to 1 setting. Yeah.
Maybe the choice of alpha ensures that, you know, the expansion operator can be made into a contraction. I guess that's my guess. Okay. Thank you.
Any other questions? Yeah. Yeah, yeah, if your step sizes are very small, the rate of convergence, like the convergence will be slower. So yeah, if your step sizes are very small, you will converge slowly. So it's hidden in the constants over here, but yeah. Just intuitively, if your step sizes are very small, convergence will be slow. Yeah. Okay. Yeah, but okay, now with z equal to 1, there are some drawbacks of this stochastic approximation algorithm. First of all, it's well known that the corresponding iterates do not have some sort of optimality. They are suboptimal in terms of what is called asymptotic variance. And in literature, people have studied Polyak averaging, which is known to give which is known to achieve that particular asymptotic optimality, or in particular in terms, the iterates, corresponding iterates are optimal in terms of asymptotic variance. So that motivated us to look at the concentration for z less than 1 case. So Polyak averaging is generally considering the stochastic approximation with step size with z less than 1, and then do the tail average of the iterates. Okay? But that requires concentration for z less than 1. So let's go to, so we do have some concentration results for z less than 1. This is what we observe. So in this case, for d less than 1, d equal to 1 and d greater than 1, we get very different tail behaviors. Again, if the operator is contractive or pseudo contraction, whatever, then you get sub-Gaussian tails. Yeah? So notice here k to the z is the rate of convergence. Since your step sizes are 1 by k to the z, you cannot expect to get faster rate of convergence. And the tail is governed by the dependence on log 1 by delta. So you get the correct rate of convergence and you get a sub-Gaussian tail. Yeah? But if d is equal to 1, you get sub-Weibulian tail. The sub-Weibulian parameter being proportional to 1 by z. Okay? So if you choose z to be very small, your step sizes are small, and you converge slowly. So you have a heavy tail, 1 by z, log 1 by delta to the power 1 by z. If d is greater than 1, so okay, so this is a very complicated expression, but what you can show is, so d less than 1, d equal to 1. If d is greater than 1, if your z is greater than 0.5, you get tails that are lighter than a Pareto tail, meaning it's not a polynomially, the tails decay faster than any polynomial, but they are heavier than a Weibull tail. If z is equal to 0.5, you get a sub-Pareto tail. Here, if z is less than 0.5, we have heavier than a Pareto tail, but there is another way to get a Pareto tail. So for z less than equal to 0.5, you can get a sub-Pareto tail. Okay? Yeah, so these are the results. So for d less than 1, you always get sub-Gaussian tail. For d equal to 1, in this case, you get a sub-Weibulian tail. And for d greater than 1, you get much heavier tails. Yeah.
Yeah, so what is the motivation for using z less than 1 given that I get weaker bounds?
Right, exactly. So that's the point. Polyak averaging, even if it has optimal asymptotic variance, its concentration is very weak.
No, but you're not averaging.
No, even after, okay, so there's a different work, very recent work by Martin Zubeldia and one of his co-authors, which says that for Polyak averaging, whatever tails you have for the iterates before averaging, that's the same tail for the average iterates. Averaging does not improve the tails.
No, but you're saying I won't get better than 1 by k power z,
Yes,
I choose,
yes.
even with average.
You may get like better dependence on the parameters, so there may be some constant improvement, but the tail behavior does not change. If it's a sub-Weibulian tail, it will be a sub-Weibulian tail, maybe with a different parameter. So maybe instead of 1 by z, it would be maybe, let's say, 1 by 2z.
No, but they have upper bounds. Are they saying?
There's also a lower bound,
They
yeah.
have lower.
Yes. So yeah, you cannot improve the tails of the iterates.
But okay, so the other question is like, does alpha depend on the parameters?
Yes, here it depends on, oh sorry, for z less than 1, I'm not sure. I'll need to check, I'm not.
The reason I'm asking is if alpha does not depend on the parameters, maybe I can implement this, have a trade-off of 1 by k power z versus 1 by k. Otherwise, there's no reason to use this step size at all.
Yeah, I guess for for z less than 1, the alpha does not depend on the problem. I may be wrong, I need to revisit that, but yeah, I guess that would be the
That was
case.
the case with the simpler TD case when I derived.
Yeah.
I get weaker rates, but I can use universal step sizes.
Right, yes. I think for z less than 1, you don't need problem-dependent alpha. But yeah, of course, yeah, you'll get a weaker rate and also heavier tails. Yeah? Okay. Sorry, how much time do I have? 20 minutes roughly. Yeah? Okay. Okay, so now let's go into, so are there any questions before we move on to the proof sketch? Okay, so let's look at the proof sketch. This is the setup that we are considering. We are solving for fixed point of this equation using this algorithm, where we assume that this is a underlying Markov, there is an ergodic Markov chain and there is an additive noise. For now, we assume that this is a bounded random variable, IID bounded random variable. And of course, we are assuming S is a finite state, so it's a bounded noise in any case. Yeah, no, yeah, thanks.
Previous slide again.
Okay,
If I ignore the 1 by k power z,
yes,
we are talking about optimal asymptotic variance and all. So are the constants better in this?
So yeah, we have not optimized over the constants at all. I don't know about the constants. We have not, we were only trying to get optimal rate of convergence and the tails. In fact, we can show that the tails, this tail behavior is almost tight. It's not exactly tight, it's almost tight.
No, I mean like in the previous slide you said, it has better asymptotic variance or something.
Yeah,
like that.
yeah,
I mean, I would expect a trade-off with 1 by k versus something
yeah.
to get better constants.
Hmm.
At least there is some Francis back working that's good.
So
But
yeah,
it's not concentration, it's expectation bound.
yeah,
So
yeah.
He gets,
So
he gets the leading term as the
Yeah.
exact exponent.
Yes,
I
yes.
guess you know the work, but I was just wondering what is a motivation to use that bound. Yeah.
Right. So yeah, we in this work we have not optimized over the constants at all. We don't know if the multiplicative constants over here, how good or bad they are. Yeah. So I really don't have an concrete answer to your question right now. Okay. Okay. Let's look at the proof sketch. So now for d greater than 1, so we will only consider the proof sketch for the harder setting, which is d greater than 1. D less than 1 equal to 1, they'll essentially follow from here. Okay. So now if d is greater than 1, the operator is expansive with positive probability. And recall our steps, if alpha k is of this form, then our bound was of this form. And if if z was less than 1, then our bound was some more complicated expression of this form. Okay. Let's see. So the proof at a high level, it proceeds in 3 steps. So in the first step, what we show is if you have an almost surely bounded sequence of iterates, suppose xk's are almost surely bounded. The bound can be increasing in k. Okay, it can be a function of k. Suppose you have this, then you can derive a high probability bound. So this bound, the original bound is it holds with probability 1. You can derive another bound which is alpha k times log 1 by delta times the old bound, and this bound holds with probability at least 1 minus delta. Okay. So now notice if alpha k is 1 by k, you are improving the original bound by a factor of k. Okay. So now, okay, so the proof of this step relies on some novel Lyapunov function in order to handle the Markovian noise. I'll show that later. But now once you have this step, in the next step what we show is, so if d is greater than 1, this property, like we may not have this true always, or the original bound may not be tight enough to give such a concentration result. Okay, so what we consider in the step 2 is we consider an auxiliary algorithm which actually has bounded iterates. Once we have the so for this auxiliary algorithm, we can call the black box reduction to step 1 and get concentration bound for this auxiliary algorithm. And then in the step 3, what we show is if you choose this the bounds in this auxiliary algorithm to be appropriately, then the auxiliary iterates and the original iterates, they coincide with high probability. Okay, so the broad proof structure is these 3 steps. So let's look at in somewhat details for each of the steps. So for the step 1, suppose you have a sequence of bounded iterates, then how do we prove such a statement? So for this, we consider a Lyapunov function which looks like this. Okay, let's ignore this log. Ideally, to prove a concentration result, you would expect to see a moment generating function, right? There are bits and pieces of that over here. It's expectation of e to the power. Think of this as the usual theta that you are familiar with, theta times xk, yeah, or xk square in this case. We need some adjustment of that in order to handle Markovian noise. Okay, so just this moment generating function itself does not work. The first bit was what was used by Chen et al. In their IID noise setting. That particular Lyapunov function, that does not work in Markovian case, only because it has a bias. The Markovian noise has bias at each time step. So to handle that bias, we need to adjust this a bit. Now, what is this adjustment term? Again, this is not at all intuitive, but this comes from something called Poisson's equation, which you also saw yesterday in some talks. And solution of Poisson's equation actually gives the correct adjustment terms magically over here. And yeah, if you use this particular function, you can show that it actually satisfies some one-step recursion. And if you open this recursion up, you can get a bound on zk. So this recursion ensures that zk's are bounded. And using this, you can construct something called martingales or super martingales and get to concentration result of this form. Okay, I'm hiding a lot of things under the rug here, but yeah, essentially coming up with this Lyapunov function is the novel step here. Okay, yeah. So this is the Lyapunov function, and once you have such a concentration result, once you have such a recursion, you can construct super martingales, you can construct appropriate super martingales, and then martingale concentration results would give a bound of this form. Okay. Now for the second step, so we consider an auxiliary algorithm which has bounded iterates. Now we have the first step as a black box. So now let's consider an auxiliary algorithm which has bounded iterates. Once we have that, you can call the step 1 and you can get concentration results for the iterates of the second step or the auxiliary algorithm. Yeah? So let's consider, okay, we don't have bounded iterates, we may not have bounded iterates. What's the natural step to do? Just project them on so that they don't blow up. Okay, so we consider this auxiliary iterate, which is, so let's say x tildes are the auxiliary algorithms iterates. So at time k plus 1, you do the one-step stochastic approximation for this auxiliary algorithm and project it onto some appropriate ball. Yeah, so pictorially, consider a ball. So recall, this is only in the analysis. You're not changing the algorithm. This is only in the analysis. So you can do whatever you want in the analysis. Yeah. So you consider a ball around x star. You can do this because this is just analysis. So consider a ball of radius b around x star. Now let's say your auxiliary iterate is somewhere here at time k. Somewhere here in time k. Perform one-step stochastic approximation for this auxiliary algorithm, meaning this update, xk plus 1. So convex combination of x tilde with the noisy output. Project it. Repeat the step. Maybe next time it's inside. Maybe then again do this, project it back. By definition, all the iterates x tildes are within this ball. They are bounded by b. Yeah? So they satisfy this bounded iterates condition. So x tilde minus x stars, these are bounded. So now, so for this auxiliary algorithm, you have bounded iterates. So step 1 will give concentration for x tilde. Yeah? Okay. Now the question is, how do we get to the concentration for x? Yeah.
What is B?
Yeah, we'll choose. Great. So that's a free parameter that we have. We'll choose that later. This is only for analysis. This is not the original algorithm. This is only analyzing the original stochastic approximation. So we can assume, in the analysis, we can assume we know x star.
So when you say almost surely bounded, it's like a sample path dependent upper bound, right? Not like a...
Right, that's fine. Yeah, yeah.
So you don't have a B for every possible...
So,
X
no,
star.
so B we'll choose later. Yeah, it will be a constant actually.
Okay, I'm curious.
Okay. Okay. So now, yeah, so this is an important point. X star is only in the analysis. We are using that only in the analysis. Algorithm is what it was. We are not using that in the algorithm. Yeah? Okay. So now, okay, so we can also prove a worst case bound for x case for the original iterates, which is of this form. This is very bad. It's increasing polynomially or even exponentially, but we still have this bound. Okay? There is an almost sure bound that you can prove that's increasing polynomially or exponentially depending on z. So now let's look at it pictorially. So we have this worst case bound that is increasing. This may be increasing exponentially or polynomially, but this holds almost surely. Yeah? Now, once you had a b, you could get b by k or b by k to the z from the first step, which is this. This bound holds with 1 minus delta probability. So both these bounds hold with probability 1 minus delta. So with 1 minus delta probability, your iterates lie in this shaded region. Yeah? Okay? Now, okay, so now this bound depends on b. This is, from here, you see that it's alpha k log 1 by delta times b. So this bound depends on b. Now, suppose if your b is somewhere here. So, yeah, I mean, b is a free parameter that you can choose, right? This requires some proof, but it is possible to choose b such that the bound actually lies above this intersection point for the corresponding decaying bound and increasing bound. Now, once you have this, what this says is, suppose you're able to choose a bound b of this form, what this says is, your auxiliary iterates were guaranteed to lie below b, right? That was the definition of auxiliary iterate. But notice, so with 1 minus delta probability, auxiliary iterates are also inside this bound. So essentially, the projection step is not active in the auxiliary algorithm because they are the maximum they can go is this with 1 minus delta probability. So on 1 minus delta probability paths, the projection, they are not hitting the boundary at all. Yeah? So the projection is not active in those 1 minus delta paths. And hence, the auxiliary iterates actually coincide with original iterates with high probability. So the concentration on these paths for the auxiliary iterates is actually the concentration for the original iterates. Yes? Okay? Yeah, I have not given B explicitly, but once you look at the bounds, that should be clear now. So these were the tail behaviors that we had for the two cases. Now, if you draw, so this is the alpha k term from there, the 1 by k and 1 by k to the z. And if you remove one of the log 1 by delta terms, you get the corresponding B. So B is a function of delta and k. Sorry, not of k, it's just a function of delta and z in the bottom case. Yeah? So it's a constant, it's not a random. So you can get a constant bound. It's very large, it depends on, it's actually log 1 by delta to the power m minus 1, whatever m was a function of d. Yeah, but yeah, again, B is also for analysis, it's not in the algorithm. So it can be any large constant that you want. Okay? Okay, any questions before?
Dumb question. So this delta, if I fix the delta in the algorithm's upper bound, then that implies a B. So can I choose two different deltas, one for B, one for the main theorem?
So actually, so B is only in the proving that upper bound.
No, but it's like with 1 minus delta. So if I choose a different delta,
Your B will be different. If you choose different
in the
delta,
theorem statement you have a high probability guarantee with say 1 minus delta.
yes,
Does that delta drive this P definition?
yes,
Or, yeah, so they both have to be same.
right, yeah. So that delta, so you first fix a delta and then you analyze the concept. So the algorithm does not depend on delta. Your concentration, so yeah, so you first fix a delta and then that delta decides what the radius of the auxiliary algorithm is. Yeah? Yeah.
So I just wanted to ask you, what's the difference between the original iterates and these auxiliary iterates? Is the auxiliary iterates using the projection, everything else is the same?
Yes.
Okay,
Yes,
so
this is the auxiliary algorithm over here. We start with the same point.
so then, if I understand correctly, what you're showing is that at one level you're showing these original iterates are bounded with high probability,
Okay.
right? And then you run like you sort of use that bound to derive the convergence rates on the original iterates itself, right? So why do you need these auxiliary iterates is not clear.
Okay, so great question. So if you see, the original iterates only satisfied this bound, which may be exponentially increasing or polynomially increasing. Let's just focus on z equal to 1 case. So you get k to the m minus 1. If you apply, if you call the step 1 once, you will get k to the power m minus 2. So that may still be increasing up to a point. Maybe after a point it becomes
So when you said that the original iterates are bounded with high probability, are they bounded at k star? What is this k star now?
Oh, this k star is nothing but the intersection point. That's a random, yeah, that's just the, yeah.
So then again my question is, when you say the original iterates are bounded, are they bounded until some time t or time k or for entire
Every k. So you can prove that under whatever the setup that we saw initially, you can prove that xk minus x star, that is of this form. That's k to the m minus 1 almost surely for every k. So it's a time uniform bound. So for every k, xk minus x star is at most some constants here times k to the m minus 1 with probability 1.
But that k is that function is growing with
Yes,
k.
so the function is growing as k. So this axis is k, so it's growing. That bound is growing.
Okay.
Yeah, you could have used this particular again and again, called step 1 again and again to arrive at a concentration result. That would give a weaker bound. So
see, I'm not sure I fully understand, but have you looked at this paper by Mukadam and Pelletier from the, for two-time scale analysis? And I think
Okay.
Pelletier has a one-time scale analysis as well.
Okay.
So there he actually uses an inductive proof which has a very similar structure to what you are describing.
Okay.
He first shows that the iterates are bounded.
Okay.
And using that fact, he incrementally, iteratively show that it can actually get better and better rates.
Okay.
So to me, it looks like the proof idea is very similar in spirit to that.
So here, actually, we are not using the inductive or bootstrapping, that kind of arguments, because we cannot, okay, that can work for z equal to 1 case, but that approach fails for z less than 1 case, unless you are able to prove something better in step 1. So in step 1, so alpha k is 1 by k to the z, the bounds, the worst case bounds for z less than 1, they are increasing exponentially, but the bootstrap or the inductive step, at least here, that will improve by 1 by k to the z. So you can never get to the concentrate, like 1 by k to the z form, because this is exponential and every time you can only improve by 1 by k to the z.
I mean, maybe we can take this offline, but you said
Sure.
that you don't need to project because the iterates remain within B. Did you make such a statement?
No. So we are considering, so okay, in the original algorithm, we are not projecting. For analysis, we are considering a projected algorithm. On 1 minus delta paths, these iterates coincide with the original algorithm. That's what, so on 1 minus delta probability paths, these auxiliary iterates, so okay, this is an almost sure bound. This holds for with probability 1, but this bound that we got for the auxiliary iterates using the step 1, that holds only on 1 minus delta paths.
So on 1 minus delta probability, the original iterates are bounded for every k. Is that correct? That's my understanding.
That would be, yeah, that would be the case. And the bound is actually whatever the concentration result gives.
Okay, maybe we can discuss
Sure,
this offline,
yeah,
but
yeah.
it looks very similar to that Mukadam Peleti,
Sure,
right?
yeah, thanks. Any other questions? Okay. Yeah, okay. So, yeah, now just to quickly wrap up, so this is, we saw everything for the bounded. We assumed that this noise was bounded, but we can in fact relax that. If we consider an assumption of this form, instead of bounded noise, if we assume that the additive noise is such that its tail is bounded by a random variable w, and you can put whatever assumptions you want on w, then we can prove again a concentration result for the corresponding stochastic approximation iterates. In particular, if you assume w is Weibulian, so Weibulian is heavier than Gaussian or exponential, but it's lighter than a Pareto tail. Okay. So if you assume that w is Weibulian with parameter theta, we get a concentration bound of this form. The parameter theta, so ideally you would expect that the square error has log 2 theta over here. We get slightly heavier than what you would expect. Okay. Yeah, so if theta is 0.5, that's a Gaussian setting, and that's one way to see that this is slightly heavier than what we would expect. If you have empirical average, again, recall empirical averages are special case. Theta equal to 0.5 corresponds to Gaussian. So if you have summation of sub-Gaussian random variables here, square, you would expect log 1 by delta here. Instead, we get log 3. Log cube of 1 by delta. So it's but yeah, what we get is at most thrice as heavy as the input noise. The tails that we can get are at most thrice as heavy as input noise. It's not clear if we can achieve, we don't have a lower bound to justify that either. Again here, the proof ideas are similar, but a different auxiliary algorithm. So the previous proof heavily relied, so the step 1 of the previous proof relied on the fact that the iterates are bounded. So here again, and that the noises are bounded, sorry, not the iterates, but the noise is bounded. So here we don't have that. So we consider again an auxiliary algorithm that actually truncates the noise so that it becomes bounded. So you truncate the noise. Now this, if you are truncating the noise, you might possibly introduce bias. Yeah. So the convergence of the auxiliary algorithm may not be to the true X star. But still we can use the previous theorems on this particular auxiliary sequence. What we can show is, so now again, as earlier you had a choice, the free parameter was B, the bound. Here you have the free parameter, which is the truncation level. If you choose truncation level to be large enough, you can show that the bias that is introduced, that is very small compared to the bound from the concentration. So essentially that's the proof idea here. Just to conclude, we saw concentration result for general stochastic approximation, and you can use it as a plug and play to your favorite algorithm. We get full tail bounds, that is we have time uniform concentrations. You can integrate those out and get moment bounds. In fact, in the paper we don't even consider like we don't even consider contraction. We can relax contraction to some extent, okay? But yeah. And the key contributions of this work are essentially, rather than just the concentration results, I would say those are some proof techniques are also new here. For example, yeah, we use the Poisson's equation to handle the Markovian noise and come up with a Lyapunov function to handle the step 1 of our original proof. And then there are 2 different auxiliary algorithms that we use to handle the different unboundedness in the iterates. Thank you.
We have time for one question.
Yeah, great talk. So I go back to the initial assumptions you had about the Lipschitz continuity of your operator. So I reduce this to an optimization setting where you have like sort of smoothness and convexity assumptions on the function. So there is some recent work on relaxing the smoothness assumption and going to generalized smoothness. So instead of a quadratic upper bound on the function, you can have polynomially growing functions as well.
Okay.
So but that is all in the ID noise setting.
Okay.
So how difficult is it to relax the Lipschitz continuity assumption?
Yeah, we need Lipschitz continuity. We need, so that assumption we need, so I'm not even sure if getting mean square error bounds without this Lipschitz continuity is possible for general F. So yeah, not sure about concentration. Yeah, thanks.
Before we close, I have a very quick question. Why not use the auxiliary algorithm as the main algorithm?
Oh, it requires knowledge of B, as Professor Shalab pointed out. The B or X, so the choice of B was dependent on X star. Like if you see the first auxiliary algorithm.
Okay.
Sorry, sorry.
You have to
project
onto
onto ball centered at
X
X star.
Okay, fine.
Yeah,
Thanks.
yeah.
All right, let's thank the speaker again.
Thank you. Thanks.
As a token of appreciation for giving this talk, I would like to hand over this memento. Okay, our next speaker is Professor Swanand Kare from, a brief introduction. Professor Swanand Kare obtained his master's and PhD from IIT Bombay, and he was a postdoc at University of Alberta from 2011 to 14. And subsequently, he joined the Department of Mathematics at IIT Kharagpur, where he is currently an associate professor. His research interests are in inverse eigenvalue problems, computational linear algebra, computational issues in deep learning, and he served as an associate editor for a journal named Control Engineering Practice, and he's also a recipient of an excellent young teacher award at IIT Kharagpur. So,
thank you. So at the outset, let me say that probably I am an outlier here. So this talk is not related to RL in any sense, okay? So this is about training and forgetting, okay? So the objective is to train efficiently and to forget also efficiently, okay? And this is with compliant MLAS pipeline. So this is machine learning as service, okay? So we see very large models being deployed on server, and then there are constraints about forgetting certain data and how we can do that efficiently possibly. So these are the two main parts of the talk, and the efficiency part is very important because this was some graph that was provided to be my research scholar who's from this source, which basically says that from the total generation of energy, about 3.5% of energy is right now required for this training tasks, okay? And is projected to go upwards by 2030, roughly 10% is what we will need. And that's huge energy requirement on this training task. So if we can do training in an efficient way, that would be very nice. And Sam Altman actually had a prediction who said that GPT-4 was, the training cost of GPT-4 was more than $100 million. So like cost-wise, energy-wise, it's a huge challenge. And being able to train efficiently is something that is really very important. Okay, so what is the basic paradigm in training? Okay, so the basic paradigm in training is that you have input data, and with respect to input data, you have model choice, and then you want to train the model with respect to input data. And these along the vertical axis are basically the samples, and these along the horizontal axis basically are the features. And what adds to complexity in training? Several things. So you might have many features in your data, huge number of features, and there is a lot of feature redundancy, and you want to get rid of that feature redundancy, get rid of complexity in the feature space, for example. The other complexity that might arise is from the number of samples. So we are still in the input data space, and you may have huge number of samples here, and many of the samples are redundant. You don't want to keep on having redundancy in your samples while training, and want to reduce the complexity in training in the sample space, still in the input. The next one is that you have a really very large model. Okay, you have a really large model, and then when you are doing inferencing, you don't need that particular very large model, and you want to simplify your model. You want to do model pruning, so to speak. So this complexity is in the space of model. And nowadays there is another added complexity that gets added, that this model that you trained locally is being deployed in the cloud server, and then some user who is providing data, like we use ChatGPT, we do thumbs up, thumbs down. So basically we are giving permission to ChatGPT to use that data to update its model, right? So like that, one day you decide, okay, I don't want my data to be used by ChatGPT. Now we have that right, and the company has to comply to our right, and then they have to remove that data. They have to remove that data from the model updation. Okay, so easier thing is just remove the data from the repository, but the model is being updated, and the model parameters also have trace of the data that you have. How do you remove that trace from model parameters? That's something that is really very important. That's unlearning paradigm. So these are the four different things that we have. So the first one is feature selection. Generally, we know that. The second one is data pruning, where you are kind of reducing your data space. The third one is model pruning, where you have a very large complex model. You are trying to reduce the complexity of that model. And the fourth one is machine unlearning. Okay. So the complexity in these four things, that's what we are really interested in. And that is basically the work of my PhD student recently submitted his thesis. These are the four important complexity issues that we looked into. And today I'm going to focus into data pruning and machine unlearning. So we will see how we can select data to do to have this complexity reduced, and then machine unlearning part. So quickly telling about this feature selection. So in this work, what we did was we did feature selection by Markov blanket process. So basically you will start increasing the features, and then you will start removing the redundant features by conditional dependence test. Okay, so some t-test was designed, and using that we were able to reduce the number of features significantly and still have a good performance. So in the data pruning, I'll explain in more details. The model pruning is something where we looked into deep networks, and then we focused on to structured pruning. So basically, we will remove as many neurons as we can based on the requirement of the user, how much sparsity in the model is required. And in order to do that, we had to come up with some way of arranging the neurons in the model in the order of importance. So we did that, and then based on, once we were able to do that, then unimportant neurons were basically clipped, and we got a smaller model. Because of the structured pruning, the architecture of the model changes, and then there were some strategies for training that particular model later on. So basically that's the summary of this model pruning, and I'll focus on to these two things, data pruning and machine learning basically. So the data pruning is basically robust, class-aware, and probabilistic dynamic data pruning. Okay. So before going into what the algorithm is, I'll just quickly tell what the notations. Okay. So this particular S is the label input and output targeted pairs. So this is my basically training data. And this xi is in some input space, and yi basically is the variable which take values between 1 to c. So I'm looking at the classification problem with C classes. And this xy comes from some basic underlying distribution of input data. And given label j from this NC, we define this subset Sj basically of all the data points with label j. Okay. And then clearly this Sj is a partition of S, and you can take the union. And the cardinality of this Sj's is Nj's. Okay, so that's I'm looking at. And then this R is basically the pruning rate supplied by the user. So what it means is that I want to keep 1 minus R times n number of samples in the data for training. So suppose somebody says, okay, this R is 0.7, then that really means that I am only going to keep 30% of the data for the training. And this is the retain set, and at each epoch t, and this cardinality of this set is 1 minus R times n. Okay, and then these are certain notations. So this alpha j is basically the fraction of the points that we'll keep in the jth class. So how many percent of data points in jth class you want to keep. And this S minus ST is basically the unused samples from the pruned set. Okay, so this is basic notation. And the idea is once the user gives you the pruning rate, then you have to select the subset of the data, best subset of the data, so that you train your model only using that data and the performance is not compromised. That's the idea. That's what basically we are trying to do. Okay, so this is one more notation slide. So just bear with me. There are a lot of things that I need. So this is f theta is any arbitrary model parameterized by theta. And this f tilde theta is basically the soft max. Okay, so that will tell me the probabilities at the penultimate layer. And based on that, I'll make a decision to which class the given sample X lies to. And then this L basically corresponds to the loss. Okay. And this is at time t. So this f tilde xi is at time t. And BP denote the batch of examples at iteration p, and mod p. The cardinality of BP is b, so that's the batch size. And then these are the basically number of elements that you will have in per batch. So basically number of iterations that you will have. Okay. So all these things I need later on to explain few things in my algorithm. And eta is basically the learning rate. Okay. So how can we reduce data? Basically the question is, I want to reduce the data so that I do my modeling as best as I can. So how can you reduce data? So there are several algorithms. So there is one algorithm which is data distillation. So in this case, what is proposed is that from the given data, they have certain means. And they generate synthetic data from the given data. And then they train the model on the synthetic data. And the claim is that when they train the model on the synthetic data, what really happens is the performance is not compromised. But the problem generally that evolves around these type of approaches is the poor generalization in practice. Okay, so on the given data, it works well, but may not generalize too well. While there is another thing, data pruning. So basically what it does is remove non-important samples from the data. Okay, so what this thing is going to do is it will remove non-important samples. But in order to determine what are non-important samples, we should have some understanding that this sample was important, this sample was not important. In order to do that, we might have to, initially do a proxy training in order to determine the importance of samples, then remove the unimportant samples, and based on the remaining important samples, you train the model. Generally, these type of techniques are found to be more suitable for generalization. They generalize well typically in practice, but these all statements are like empirical, tested on a lot of data sets, and this pattern is being observed. Okay. So typically what is expected in data pruning is this. So this particular thing here, this is the model that you obtain after pruning. Okay, so this is the data set X, Y. So this is pruned data. And this was the model that you trained. So this is the model that you trained after pruning the data. And this was the original model. If you had just look at the loss values, there was a big model with all the data and you trained it and you saw what was the loss value for this particular data pair. And then on the pruned model, what is the loss value? What would we expect to do is that for the model with the pruned data, we should, so this loss value should not be too far away from each other. That's what we are trying to match, right? So these loss values should be similar. So that's the objective that typically any data pruning approach will have. And then there are two types of data pruning that generally are aware. One is static pruning. So in the static pruning, what really happens is that they will actually prune the data set a priori. Like they will decide beforehand that this data is important, this data is not important. And then they will remove the data which is not important and use only the data which is important, and then you work with that data to train the model. But dynamic data pruning is basically periodically selecting a subset during training. So what is happening is you keep entire data with you, but every epoch when you pass the data, you do not pass the whole data. You will select the subset of the data that you want to pass for that epoch, pass it, and then do it. Okay, so that's dynamic. So it might happen that you will have different subsets to pass at different epochs. Okay, but that's something that we want to look into. Okay, so what I'm going to focus on is dynamic. So you are not going to lose out on the entire data set, right? So here, once you discard, that data is not available for training, but here that data might come up, we don't know yet. Okay, so in both the cases, the percentage of the data that is used in every epoch to train is determined by the user. So that is something that is guaranteed. Okay. So what happens in static versus dynamic dataset pruning? So you require low storage cost because a lot of data is actually thrown out, and the high compute cost because initially you have to do a proxy training to determine which data are important or not, and then you have to train the model again. And the transferability. So if you want to use this model for some other transfer learning these things paradigms, the data that you chose, how good it is, that's questionable. Okay, it might not be very good. Whereas in dynamic data set pruning, high storage cost because you still have to store the entire data, but the computation cost compared to this is low, and generalizability is to specific models. Okay, in certain models it really generalizes well. Okay. And one of the important advantages of dynamic dataset pruning is that it seems that it beats neural scaling laws. Okay, so I will not go into details of this, but there is work here in this paper which basically says that if you exponentially increase any one of the complexities that we earlier saw, basically the complexity of the model, the data, or the compute, how long you will run your model, you can reduce the loss. If you increase the data or if you increase the complexity of the model, then you can decrease the loss, but the loss never seemed to go beyond this. So basically what it says is that exponential increase in these inputs results only in linear decay in the loss. Okay, so that linear decay in the loss you cannot beat, but it seems that if you choose your data cleverly before training, then in some cases you can beat this particular paradigm. Okay, so this is something interesting, though I will not go deeper into this in this particular talk, but that's something that is interesting. Okay, so now coming to this dynamic dataset pruning, there are certain limitations about the methods that we already have in the literature. So for example, in the case when you have balanced groups, okay, in the training there are C classes, they are balanced, then for a particular model, it's not that all the groups are equally easy or equally difficult, right? There are certain groups which are easy, there are certain groups which are difficult for the particular model to classify. So what is easy, what is difficult depends on the model, but there are certain easy classes. So for example, in the example that I have here, so ResNet 18 trained on CIFAR 10, 95.3 is average accuracy. But the best performing class is the class of aeroplanes where 99.87% of accuracy is observed, while the worst performing class is the class of cats where you see the accuracy drop to 92%. So for this particular model, for this particular data case, it looks like this cat class is like the worst performing class. Okay. So this is something that I would like my dynamic data selection to keep in mind, right? So that is something that is important for my algorithm. Generally is not looked into. And the other one is imbalanced data setting. So in the imbalanced data setting, classes can be highly imbalanced. So for example, in this iNaturalist data set, the majority class has 1,58,000 examples of this particular thing. But the minority class, which is Protozoa, has only 308 examples. There is huge imparity between the two classes, right? They are extremely imbalanced. So I would like my dynamic data selection pruning to pay attention to these two things also. So one is the imbalanced data, the other is the balanced data, but some classes are easy, some classes are difficult. So if you want to relate this to our usual learning experience, so for example, all of us prepare for exams and there are textbooks, math problems are there. Okay, so it might turn out that on 10 topics, all the problems, every topic has 15 problems. That's how typically the assignments are handed out by teachers to you for your courses, right? So one student might think one particular topic is easy, one particular topic is difficult. If the topic is difficult, student wants to give more importance to the assignment, which is difficult, right? So if you decide to work out only 5 problems, in the entire semester, out of 50 problems that were given to you by the instructor, in those 5 problems, you will tend to choose the problems which you think were difficult for you to solve. And the easy problems are little less, right? So that's what I would also want this dynamic data set pruning to follow. The difficult problems, I want more in my sample, and easier problems, I want less in my sample. At the same time, I have to look for this imbalanced data set. So like one assignment has 50 problems, other has only 10 problems. If you want to solve only 15 problems, you will tend to solve more problems from the second assignment than the first assignment. That's the imbalance thing. That's something that we always do. So that's what I want this algorithm to actually imitate. Okay. So that's what I want to do. So now with this in mind, what I want to do is 2 things. So I want to determine how many samples per class I will choose when I'm pruning the data. So which class should have more samples, which class should have less samples, how many samples per class. So I have to determine per class samples. And once I settle that issue, then I have to say, okay, from this particular class, I want to choose certain number of samples. Which samples from that class I should choose now? So how many per class? And once I settle the issue of how many per class, which from that particular class? Okay, so these are the 2 things that I'll try to settle now. So that is where I will need all the notation that I had introduced. So basically, if you define your total empirical error by this particular thing, where this you can see this EJ tilde is basically loss of F theta xk tilde, where Sj tilde is a subset of Sj. I choose any subset Sj tilde of Sj. And the proportion is basically this. And then I basically take the weighted average of all this every class empirical errors. Then this is E. Then my objective, so these numbers are fixed, right? So this Pj, Nj, and these loss values, once you decide the subset, they're all fixed. The only variable is alpha j. So this alpha j is basically telling you how many percent of samples from the jth class you are choosing. So that's alpha j. So the freedom is on that alpha j, and it is basically telling me, so I want to minimize this E with respect to this alpha j. Okay, so what percentage of what factor of samples from each class I should choose so that I'll minimize this E. That's the problem that I am trying to solve. So of course this is with the constraint that this alpha j nj should all sum up to 1 minus r times n, where this 1 minus r times n was the number of samples I was allowed to keep. Okay. So if you want to solve this problem as a free variable or a decision variable with alpha j, then what we are saying is that this particular problem has a minimum which is given at this particular choice of alpha j, which is root of pj ej tilde divided by sum of root of pj ej tilde multiplied by this 1 minus r n by nj. Okay. So this is something that is very interesting. How many samples per class, right? That's the question that this particular thing is saying. So for example, you consider the case where all the classes were kind of same in size. So nj is same throughout. So this particular factor 1 minus r n by nj, this particular factor is actually kind of constant in the case of balanced data points. And then this factor comes into the picture, and this factor is basically telling, so this is the error at the jth class, so to speak, this is the total error that you are committing. So if you are committing more error in the jth class, then you are saying you choose more samples, because that for that place alpha j value will be larger. So the intuition that we had, that harder class should end up with more number of samples, that actually kind of is clear from this particular case. On the other hand, if there is very high imbalance in the data, for example, nj is extremely small for class j and for some other class it's extremely large, this n by nj is accordingly large or small because 1 by nj factor, and then that tells you that the percentage or the fraction of the samples that you want to keep in case of unbalanced class, how they work out. So intuitively what we thought should happen actually is happening if you set your optimization problem in this particular way. So the proof is not very difficult, it's just Lagrangian. So you can build the Lagrangian, and once you build the Lagrangian, you take derivative of Lagrangian with respect to this parameter alpha j, then you get this expression, and then the constraint, you substitute that in constraint, that will give you this particular thing, right? So this theorem is a key theorem that is going to help us in implementation. So when you do actually implementation, what we do is that we use this particular equation that we had in the previous slide. So this is the equation that we will use. So this equation will be used as the fraction of samples that I want to keep in the next iteration based on the losses that I have at this particular thing. So this is the key equation that helps me to implement my algorithm. So this alpha hat t plus 1, this is what is going to happen, okay. And once again repeating, allocate more number of samples to current epoch's worst performing classes, right? That's what we are doing through this particular optimization. And then there is some issue that alpha hat j value might be bigger than 1. If that is bigger than 1, then there is a small adjustment that you need to make. I think it's okay, we don't need to go into this detail. We can take it later on if we want to. And now once we have decided per class how many samples I want to choose, then the next question is which samples I want to choose from that particular class. Okay. So how many is that? Yeah.
So I just had a question. So in that your EJ is like your training loss or validation loss, or what is it?
So it's training.
It's training loss.
Yeah, in training you are doing this.
Okay.
So this is everything is happening while you are training. It's training loss, and then in training you are deciding in next epoch which subset of data will go for training. So that subset where in this particular epoch you did not do well, those points, more of those points in the next epoch.
But doesn't that mean your objective that you are minimizing keeps changing with epoch to epoch? Does it make like a fair comparison? It's not clear to me.
Can you repeat the question?
I mean, your objective function,
yeah,
right, changes from epoch to epoch, right? Because
yeah,
you're
so that's
looking
why
at the error with different set of samples, and it's not clear to me if you are minimizing.
No, so that's why we say expected, like the objective is to minimize, like this expectation should be as close to 0 as possible. So in the expected value, so you are right. So while we are actually doing training exercise, we are only presenting one instance of what you are saying. You are right. So when actual training happens, only one instance of this thing is presented. But yeah, in principle, what you are saying is right. And now per class samples, how many per class? That's the question now we want to ask. So once again, going back, what we wanted is that this is the model on the prune data, and this is the model on the entire data. So this upper tilde basically means softmax. I want these two values in the expected value as close to each other as possible. That's the objective. And then I just open up this theta t and theta tilde t. So theta t is the parameter. So I just open it up and I use the recursion. Okay, so this is my gradient descent algorithm, which is opened up and written in terms of initial theta 1 and final the theta t epoch. And this basically is the learning rate, and this is the batch size, and this is the number of epochs, right? So how many iterations will happen per epoch. So this is the standard expression that we see here everywhere. And the same goes for theta tilde also. So that is also the same thing that I have here. And then what I do is the following. Okay, so for the sake of ease of notation, I take this inner summation that I have here. So I take this thing as the gradient. Okay, so basically I replace this by some notation. I replace this by some notation. That is basically the gradient. So I call it GTP and G tilde TP in both the cases. And then under the assumption that the loss is Lipschitz continuous, this L of F tilde theta, I call K1 to be the Lipschitz constant. And under this condition of Lipschitz continuity, I can now basically take the expectation on both sides, and then I replace this theta t and theta t with this particular notation of GT. What I find out is that this is the entity that I was interested in. I want to make this entity as small as possible, is basically bounded above by this particular number. And this particular number which bounds the entity that I am interested in through the differences between the gradients. Okay, so if I want to make this particular number, this particular expectation as small as possible, I want to now decide which terms in this will go to 0. So basically the gradients which are more, so the examples for which the gradients are more, those examples if I consider here in G tilde, then those dominant gradients will cancel each other out in this summation, and I am left with smaller gradients that I cannot do anything about, right? So the idea of choosing the samples is choose those samples for which the gradients are really very large. That's what I will do. Okay, so that's the idea. So this particular equation actually gives that idea to me, that choose those samples for which the gradients are really very large. But in typical implementations, having the gradient information is really very difficult. So what we do is what can we use to proxy these gradients? That's the question that we ask. And what we basically do here is that through some small case studies and prior work, what we basically do is we relate the loss of a sample with the gradient magnitude. Okay, and we see that typically the higher gradient comes with the samples which have higher loss. And as I mean, I'm not saying what causes what, I'm saying there is a correlation, there is high correlation. High values of loss are highly correlated with high value of gradient, and so on and so forth. Okay, so this is basically the one particular simple example where you can see that this particular sample had high cross entropy loss and high gradient value, and as epochs go further, you can see that the loss actually goes down, and smaller loss is highly correlated with smaller values of gradients. Okay, there is, I'm not saying this always is true, but generally there is a high correlation that is observed between these two things. And in this paper also they had observed this thing. So what we do is, instead of looking at gradients, we proxy the gradients with the loss values, and that's how we can make that equation implementable. Okay, so in place of these gradient values, we'll substitute loss values, and the loss values which are higher for those examples, we'll keep those examples in our data set. Okay, so which examples to keep? High loss examples, so that this number will be smaller, so that you will commit less error. So that's the idea. So roughly speaking, high loss examples are the difficult examples. So which examples to keep? The more difficult examples to keep. So that's the justification for that. And then maybe these implementation details I will not go into, but I'll just say that you start your algorithm, and then what really happens is you choose the fraction of the data you want to keep at that particular epoch for each class, and then which samples to keep, and use that to train your model. After model training, you update your values of losses once again. Now in next epoch, certain examples might be difficult, which were not difficult in the earlier epoch. So they come into the play, and in this way you can keep on using the entire data, but the fraction of it at every epoch. Okay, so that's the idea in dynamic settings. So two things: how many samples per class, that will also be decided at every iteration, and which sample based on the loss values at that particular thing. Okay, so a quick run through the results. So these were the different data sets that were used, Cypher 10, Cypher 100, ImageNet. So these are the data descriptions, and the models that were used was ResNet 18 in first two cases, the INO V2B. So there it is already a pre-trained model, only the last layer was taken out, and this thousand layer fully connected last layer was trained. Basically, that's what we did in this third case. And these are the highly imbalanced data sets: Waterbird, Celebi, and iNaturalist. And these are the models that were used. And I mean, it's a huge table, but what we have to see is two things: the worst class, the worst group accuracy. So these are the results for worst group accuracy. So worst group for a particular model, once you train, you know, and after data pruning, how that works for all the methods. That's what we saw. So you can see that almost all cases, the worst group accuracy of our model actually is much better than the worst group accuracy in the other cases. Okay, so that is something that is really important. You are doing very well in the worst group. So the model had a particular class which was difficult for it. So you are actually making good, you are still doing good on the worst group than the other methods. Okay, so that was something that was more important. And then average accuracy also you can see. So average accuracy is also fairly good, and in most cases the average accuracy is comparable. But now this is the place where we can say that why I am not able to beat the average accuracy is because now I am giving more importance to the samples which were difficult for me to learn. So I took more data from there and little less data from the good samples, so to speak. So less data on good samples still got me the average accuracy, which was kind of comparable with the previous things, right? So that's what we see from this particular thing. And this is a very interesting aberration study. So through actually the example, so if you look at this Waterbirds data, and I think 2,400 samples, 2399 or 2400, that is the number of samples I wanted to keep. Then you can see at 50% what is happening. So this our method initially in the first epoch kept 1835 samples, okay. And as the epochs progressed, this was the bigger class. You can see roughly about 450 samples are now kept here. Whereas this the smaller class, it started with 564 samples, and then it finally increased to roughly 850 to 90 samples on an average. Okay, but if you see the other methods, you can see that 1842 was the starting point. Roughly 1800 samples throughout it has kept. And in the imbalance class, the class size where it was smaller, it started with this 556 samples and it roughly stays around 550. Okay. So you can see here the jump in the samples, roughly 300 to 400 more samples from the smaller class were picked, which is not happening in the second method. And that's the reason. Okay, so that is the reason why we are able to get better performance even in the imbalance classes or difficult classes. Okay, so that is something that we can actually study, see from this aberration study also. Okay, so in summary, what we have done is that we have proposed the data pruning algorithm. But the problem with this, the limitation is this, is that the way we work this around works only for classification tasks. Okay, so immediate next thing is to, can we do this for non-classification tasks? So that's something that we need to look at. And then I have not added this, but recently my PhD student Atif actually put a GitHub repository for this particular thing. So this entire thing and all the case studies, like all the other data sets and other methods that we had used, they're all present in that repository. You can try your own data sets and model. I think it's fairly good. So you can definitely try that GitHub repository for actually trying out these things. And if you find any problems or notice something is not working, please get back to us, and then we'll be happy to do the corrections. So The other part was, so this was offline model training, how to bring in efficiency in that. And now the other thing is that once you deploy the trained model, then how do you unlearn, so to speak, right? So this right to be forgotten, I think I'll skip. I already told that what to do. Okay. So generally what is happening? So this is the training data set that we have. And this part of the data is like forget data. So I want to forget this data. And then this is the remaining data. So if I really want to model if I really want to forget the data, I will just delete this data. And if I want to erase the influence of this data on the model, what ideally I would do is that with this data, I will retrain again. The entire model I'll retrain again. Okay. So that's like my gold standard, but that's absolutely inefficient, right? If somebody comes and says, okay, delete this 50 data points, I cannot keep on doing this, delete and then retrain the entire model. But this is my gold standard. This is what I will always want to have, right? And here the model is trained, and now somehow what I want to do, this forget data should do something so that I remove the effect of this forget data on this trained model that I have. And this is the unlearned model, so to speak, I get. And this unlearned model should be as close to this retrained model as possible, right? So this gold standard is what I'll always compare against, and I'll see how good the performance is of my model, unlearned model that I have, right? So that's the objective. That's what is really going to happen. And then there are two paradigms, approximate unlearning and exact unlearning in literature, where people try to come up with unlearning strategies, where you will get exactly the model which you would have retrained and the approximate one. So the models like recursive least squares and all, they're very easy. So I had a student working with me where we could actually generate the exact unlearned model from the data because of the updating QR decomposition approach that we have in linear algebra. That was easy, but it's not always easy for the large models. So there are certain approaches. One of the famous ones is CISA. So basically what you do is you divide your data into fragments, and then what you do is here you take D21 and you train your model for n epochs with only D21, and then you stop. Okay, you store this model, and then you add data D21 and D11 together, and then you train for the next 10 epochs. Then you take a snapshot here and stop and keep on doing this. That's what you do. So you have different snapshots here. And then now if the request comes that I want to forget some data point from D23, then what you do, you look up to this snapshot, all other snapshots go from here, then you combine them, and once you combine, that's the model that you would like to view. But now you can see that this is a very difficult task, right? This is a very difficult task, right? Like you have to train so many models with so many things, and you have to keep things. So this is one-time thing though, but it's a huge effort that one has to take. And the other one is label agnostic forgetting. So this is something that comes close to what we have done. So here the assumption is that they don't require the labels of the forget data that they want to forget. And the two different losses are basically combined. So one is this variational loss, typically using autoencoders, they try to minimize the change in the representations of the data that will not be forgotten. And this is the extractor unlearning loss, where they will try to match the predictions of the data that you want to retain. And then these two losses are basically combined in order to build the unlearn model. Okay, so that's the loss in the unlearning process. So these are two of the most and recent works that we have. So once again, limitations of current methods. So exact methods are too slow, and it's not possible in general to have exact methods. And approximate methods are fast, but what really happens is that they require access to the remaining data. So access to the remaining data is a huge thing. It might be huge, it's difficult to handle. Proprietary reasons will prevent you to have access to this data. Okay, and also many of the methods require labels of the data that you want to forget. That's also something that may not be available to you. So what does ideal machine unlearning should do? It should be label agnostic, no need to have labels for the forget data, and requires access only to forgetting data. Whatever data you want to forget, you should have access to at least that. and it should be robust to adversarial threats. Okay, so this is something that is an important issue in MLAS. So you can design an adversarial attack by feeding out input strategically designed in such a way that the output of that inverse attack will actually try to recreate the data that you used for training. And if that happens, then you are kind of compromising the privacy of the data. So we are using these things to check if the malicious user will be able to recreate the forget data. If the forget data is being able to recreate, then our unlearning algorithm is not really very good. Okay, so that should not happen. So that's what we will try to check. So ideally this also should happen. Okay. So this is the paradigm of this MLAS. So this is the service provider who has this big model, and this is the training data, and these are two types of users. One is authorized user and the other is authorized but malicious. They give data for model training and then they later on request data to be forgotten, and then we apply some unlearning algorithm, and then this is the unlearn model. Okay, so normal user will query, the unlearn model will give the output, but once again the malicious user will design queries in such a way that it will try to reconstruct the input data. And what we want to do is we want to make sure that even if somebody is trying to do that, our unlearn model will not be able to reproduce fragments or the entire data that was used while training. Okay, so that's something that we want to look at. So unlearning meaning, so how do we actually solve this? So the way we solve it is not very difficult. It's very intuitive. So the first thing is we want to actually unlearn. So when we say unlearn, the data, if I pass through the unlearned model, it should have low confidence on predictions, right? So whatever the learned model predicted, I should not have that high confidence on the prediction in the unlearned model. So I want to do some assignment of probabilities, right? So I have to change my probabilities in the loss. That's what I will do. And then no performance degradation on the data that I did not want to forget. So while doing this, I should also make sure that the model that I will get as an unlearned model should continue to work very good, at least as good as it was working previously on the data that is remaining. Because if it starts working badly for the data that I am retaining, then that's not something that I was looking for, right? I forgot, but I forgot much more than what I was supposed to forget, right? So that's the balance that I want to strike. I want to forget what I want to forget. At the same time, I want to be as good as I was on the data which is remaining, right? So that's the challenge. So the first part amounts to probability redistribution in the softmax layer, and the second part is the regularized loss that actually we will introduce. Okay, so this is the probability assignment. So this probability assignment, this technical formula is not important. The concept is that the data point which you want to forget should not come out, should not have the probability distribution as you had earlier, right? Roughly uniform distribution if you have, then you don't have to you have forgotten it well, basically. That's what. So this is the effective unlearning loss that we define. So the first term is the KL divergence between the reassigned probabilities after unlearning, and this was the probabilities that you would get for the data, and you want to see that so this is what you want your model to predict, and this is what you have decided should be happening, right? So you want to minimize the difference between these two through KL divergence. So this part will amount to unlearning, and this part basically says that I don't want to deviate too much from the model parameters that I have already learned, because if I deviate too much from the model parameters I have learned, then I will start performing badly on the retained data. I don't want that to happen, right? So I want to minimally move away from the current model parameters, still being able to forget this. So these are two conflicting losses. So these are the hyperparameters basically that you will have to choose properly so that you are not doing too much of unlearning or not doing unlearning. Okay, so these lambdas you have to choose carefully. So this is one problem in this, that you have to really be able to carefully choose these lambdas. Okay, so this hyperparameter selection becomes a key issue here, and there is a strategy for hyperparameter selection that we have given here, and we use this cosine annealing to make sure that you don't forget too quickly or you don't keep on retaining your model. So you want to forget gradually, give space for model to forget while not moving too far away from your model parameters. Slowly you do. In one go you do this, then everything gets disturbed quickly. So that's the annealing, cosine annealing update on the hyperparameters that we suggested. And then there is this lambda min, lambda max per layer. We just change linearly. So we make minimal change and maximal change on the penultimate and the first layer respectively, right? So that's the idea that we do. And then once again, these are the 6 performance matrix that actually we look at. So this forgetting accuracy on the training data set should be low, retain accuracy on the training data set should be high. Forgetting accuracy on the test set should be low, retain accuracy on the test set should be high, test accuracy total, average of all these things. And then the membership inference attack, in the sense that if you were attacked malicious user, then they should not be able to identify whether this image was in the data set or not. So ideally the value should be 50%. That means the attacker does not know for sure, it's 50%. That's the best value that you can have here. And the computational efficiency, how quickly you are able to achieve this. Okay, so once again, these are the controlled simulations on synthetic data sets. So what these are, like, these are two like well-known data sets. This is Moon's data set. So here there are 3 classes, and amongst these 3 classes, I choose to forget this entire class, blue class. Okay, that's what I choose to forget. So if you see, when I trained the model, this was the decision boundary that I had. And then what I want to do is I want to forget this green class. So what I did, I removed that green class and I retrained the model once again. That's like my gold standard. And after doing that, you can see this was the boundary that I got, decision boundary, and apply the unlearning algorithm that was proposed. And then you can see that the decision boundary is this, and you get fairly good thing that is going on here. So that is the class-wise forgetting paradigm. And it might happen that you don't want to forget the class, you just want to forget certain samples. So if you want to forget certain samples only and not the entire class, then how does this work? This works with this. So this was the gold standard. Once again, retrained model by removing the forgetting data. And these are the decision boundaries. You can see they fairly work well. And the same thing that is presented for this blobs data set. So this is class inside class. So this is typically a difficult problem. So this class is forgotten. You see, you still are doing well. Or if you forget samples, then also decision boundary is altered, but it's not very bad. You still get good performance. Okay, so this was on control simulation case. And in some other big data sets, so use 3 data sets, SAFR10, SVHN, and Tiny ImageNet. And these are the data set descriptions and the models that we use. And then you can see, compared to all the matrix that we had and all the methods that we compared against, you can see typically everywhere the average accuracy that you see is reasonably well for the model that we are working with. Okay, so you can see that our model performs well. Not only that, you look at this membership inference attack, most of the times our value is very close to 50% compared to other models. The only thing is that we do not perform really very well on SVHN dataset, and we see this consistently throughout all the examples. But apart from that, this model seems to work well on the other 2 datasets. And this is the paradigm of sample-wise unlearning. Again, the same phenomenon you can observe. And so quickly about the robustness to adversarial attacks. Okay, so now this is the thing that I have. Okay, so this is the attack that I use, mirror state-of-the-art black box model inversion attack. And this is the forgetting class. So these are the images of the same person, and these are the images of the same person. And I want to forget this class, so I want to forget this person. So if you do sample recovery using this MI on the initial model, then you can see that I am able to reconstruct these images for this class and these images for this class. Fairly good reconstruction of the image, right? Now I decide to forget this class, so I forget this class. And on the unlearned model, if I apply the attack, on the unlearn model, if I apply the attack, then you can see that the data, the unlearn on the unlearn model was produced is completely different. Okay, so the image reconstruction is completely different in this sense. Here also it changes, but not much. It's still okay, right? So that's the robustness to this inversion attack. So on the unlearn model, so I am not able to recreate the data that was forgotten. So that was the objective. You can see that after applying repeatedly, I am able to get this as my data that might have been used to recreate, which is not clearly the image that I had. So this simulation kind of is empirical proof of this method is actually robust also. And another interesting thing is visualizing how actually unlearning is happening. So these are the images of walrus, and this is the class which actually I want to forget, and these are the non-forgetting things. So ground truth activation maps for the first model, which was total model, you can see that these were the activation maps, means that my classification of walrus was correctly done by these activation maps. Here also this mobile phone, pan, butterfly, they were correctly observed. Now I decide to forget this class and then I do unlearning. And on unlearned model, when I look at the activation map, you can see the activation map is over all places in case of walrus. When it is predicting what this image is, it's obviously not able to predict the activation is all over places. But at the same time, you can see the activation map on these three images still is very good. So on the retained data, you still are working well, while on the forget data, you are not really doing well. So the unlearned model on forget data is actually really behaving poorly. That's another way of looking at it. Okay. So in summary, we have proposed a model which is really very fast. Okay, so in the results, I did not emphasize on the fast aspect. So I will just quickly show the number of iterations. You can see these are the number of iterations, and you can see we are like really very low compared to iterations that other models require. So we are able to unlearn very fast. So that is something that we wanted to achieve, and we are able to achieve that also. So in summary, that's what we have been able to do: fast, robust because it's robust to the attacks. The limitation of this is that it requires careful choice of hyperparameters. So that is something that is not a good thing to have for an algorithm, but in this particular case, we see that this is really the critical case. And this is once again done only for images and classification tasks. We would like to develop further for generative AI type of models. Okay. So for this also GitHub repository is available. I forgot to put the link for the GitHub repository, but you can have the look at the GitHub repository, use the codes and try to do the unlearning. Okay. So that's where I'll stop. Thank you. Thank you for your attention. Any questions if you want?
We have time for a question.
Yeah.
Hello. Sir, I have a doubt query regarding the data pruning thing.
Huh.
So in the data pruning, what is a strategy that you're taking in order to do the oversampling of, high error classes? Because if we choose random oversampling, that particular images will be duplicated and it will lead to poor generalization of the model.
No, so we are not doing that. So we are basically deciding based on the loss values which images to choose. So the losses are arranged in the order, and then we choose those images.
So if particular class has more losses,
Yeah.
there was one table where the particular class has been oversampled, let's say from 500.
So by oversampling, you mean more samples from that particular class? Yeah, yeah. So that is governed by the result, theoretical result that we show. How many samples? So that alpha j you have to choose. So that is given by this particular theorem. So okay, so this was the result which actually told you why it will happen. Sorry, it is taking forever to go back, but. So this is the result. So this was the theorem. So we proved this theorem through optimization setting here.
Yes,
So this result basically tells you how many samples.
that's what. My query was exactly like, let's say this theorem says to have more samples on one class,
Yeah.
let's say class 1,
Yeah.
and we are adding more images of that particular class.
Yeah.
That methods can be, let's say, for image augmentation or random oversampling of, let's say, duplicating the same
No,
class
no,
images.
no, 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 no. We are not doing that.
Right.
Okay, so in the interest of time,
Thank
we
you,
can
sir.
take the rest of the questions offline.
Yeah,
As a
sure.
token of appreciation for giving this talk, I'd like to present this moment.
Thanks.
Okay, this brings us to the end of this workshop. We have the feedback form. So this feedback form is standing between you and lunch. I request that you give this feedback. It's very important because the funding agencies require this in our reports. So please provide your feedback. Okay, and while you are providing this feedback, I would like to take this opportunity to thank everyone who made this workshop a success. So first of all, thanks a lot to each one of you, and especially to the speakers who gave their time in sharing their knowledge with us. Apart from them, I would like to extend some special thanks to two people who made this workshop move on smoothly. The first among them is Kushal. Can you please come on the stage? I think she has been the one who has moving from one place to another to make everything available on the spot at the right time. So let's give her a big round of applause. I next request Sanjay to please come on the stage. He's the one who is managing the technical side of these things, including ensuring that the workshop is broadcasted live on YouTube. So let's extend a big round of applause for him as well. Okay, finally, we have a bunch of student volunteers who have been, ensuring all the nitty-gritties are taken care of. I would like to now request each one of them to come on stage. So first is Girik, next we have Anirudh, then we have Nibedita, and the last is Aditya. If you're around, please come on the stage. You can just move there, okay? All right. So I request once again that please provide your valuable feedback, okay? And then after you are done, you are free to move on and have lunch. Thank you.